quiet corner of the internet where curiosity drifts hand in hand with calm. Whether you're settling into bed, listening in the background, or simply letting your mind unwind, tonight's journey will take us into one of the strangest and most beautiful frontiers in science: quantum chemistry. It's the study of how the tiniest pieces of matter behave when no one's looking, where electrons blur into waves and bonds form through invisible dances of probability. It's the hidden architecture behind everything solid, soft, or living, from the air you breathe to the light that reaches your eyes. Before we begin, I'd love to know where you're listening from. It's always fascinating to see how far these quiet explorations travel, from midnight bedrooms to early morning commutes across the world. If this calm dive into science helps you relax or sparks a little curiosity, please do consider giving the video a like and subscribing to the channel. And for those of you already part of the Sleepy Scientist community, thank you for returning. It means a lot. Just remember to gently tap the notification bell so you won't miss the next peaceful exploration. And of course, I hope this video isn't too interesting that it keeps you awake. But if it does, at least you'll fall asleep a little wiser than before. So, as the world outside quiets and the glow of your screen softens, let's begin with a simple question. What happens when chemistry stops behaving like matter and starts behaving like light? Quantum chemistry lives in the space between certainty and possibility, the realm where equations describe clouds of probability and where atoms, though invisible, reveal their patterns through light and energy. In classical chemistry, we once imagined electrons as planets circling a miniature sun, neat, predictable, obedient. But the deeper scientists looked, the more the universe refused to stay still. At the atomic scale, certainty dissolves. Position and momentum cannot both be known. Energy comes only in discrete steps, and the same particle can behave like a wave, depending on how gently you ask the question. This strange foundation doesn't just exist for curiosity's sake. It explains everything chemistry truly is. Why hydrogen and oxygen combine to make water. Why iron shines and carbon builds the framework of life. Even why the blue of the sky differs from the green of leaves. Quantum chemistry takes the equations of quantum mechanics, once thought far too abstract, and applies them to the messy molecular world. It lets scientists predict the shape of a molecule before it's made, the color of a crystal before it forms, or the strength of a bond before atoms ever meet. It connects the vast cosmos of physical laws with the gentle intimacy of chemical reactions. It's a field that whispers rather than shouts. Every calculation is a quiet conversation between wave and particle, every molecule a symphony of invisible interactions. And despite its complexity, it's built upon a single, profound truth, that matter is not solid, but structured energy. In this calm exploration, we'll walk through that structure, from the shapes of orbitals to the glow of light, from the bonds that hold the world together to the quantum rules that sometimes let them slip apart. There will be no rush, no clutter, just clear, slow understanding. So take a breath, let the day fade into background static, and imagine for a moment that every object around you, every atom, every spark of light, is playing by rules that are beautifully uncertain and yet perfectly consistent. That's the quiet world of quantum chemistry, and tonight we're going to explore it, slowly. At the turn of the 20th century, something quietly revolutionary happened. For centuries, scientists believed energy flowed smoothly, like water down a hill, continuous, unbroken, predictable. Then, in the year 1900, a German physicist named Max Planck noticed that the math behind glowing metal didn't quite add up. To make it work, he proposed something outrageous for his time, that energy comes in tiny, indivisible packets, quanta, not a steady stream but discrete jumps, like coins instead of a sliding scale, or the rungs of a ladder rather than a ramp. It was a small adjustment that cracked open an entirely new world. That single insight changed everything. Because if energy could only be traded in specific chunks, then atoms couldn't absorb or release just any amount they liked. They had to take or give whole packets, one quantum at a time. Suddenly the universe seemed pixelated, and though Planck himself didn't yet know it, this quiet idea would become the foundation of quantum mechanics, and eventually the chemistry that builds every molecule you've ever touched. Imagine for a moment a staircase in the dark. You can move up or down by stepping onto each solid rung, but there are no steps in between. That's what energy levels are like for electrons. They can jump from one rung to another, but never rest halfway. Those jumps, those quantum leaps, release or absorb light. Every atom, every element has its own unique set of rungs, like a private tune. This is why, when hydrogen gas is heated, it doesn't glow with a smear of colour, but with clean, crisp lines of red, blue, and violet. Those bright stripes in hydrogen's spectrum are the visible footprints of electrons changing energy levels. Each leap creates a precise colour, a photon of light released as the electron settles into a lower, more comfortable state. If you could listen to them instead of see them, every element would play its own distinct musical scale. The great puzzle, of course, was how to describe this new invisible behaviour. That task fell to a quiet Austrian physicist named Erwin Schrödinger. In 1926 he wrote an equation, a strange sinuous thing, that treated electrons not as particles racing around a nucleus, but as waves spread through space. This equation didn't tell you where an electron was, only the regions where it was likely to be found. The wave described a probability, a smudge of existence. This idea, that the building blocks of matter behave more like waves of possibility than tiny marbles, is the essence of quantum chemistry. An electron isn't a dot orbiting like a miniature planet. It's a cloud of maybe, a shimmering presence that thickens in some places and thins in others. The denser the cloud, the higher the chance of finding it there. These clouds, called wave functions, are like the universe's secret blueprints. Each one describes how an electron behaves in its atomic home. The shapes we call orbitals. Some are spherical, some shaped like dumbbells, others like delicate clovers. Together they form the invisible geometry of atoms. When two atoms approach, their clouds overlap and form new ones, bonds, the very foundation of molecules. But before bonding, before chemistry itself, comes uncertainty, the rule that defines everything in the quantum world. In 1927, Werner Heisenberg realized that no matter how clever you are, you can never know both an electron's position and its momentum with perfect precision. The more clearly you see one, the blurrier the other becomes. It's not a flaw in measurement, it's a feature of nature itself. Think of it as the universe's way of protecting its privacy. If you try to pin down an electron's exact location, you lose sight of how it moves. Focus on its speed, and its place dissolves into a haze. Reality, it seems, doesn't like to be over-defined, and strangely enough, this uncertainty is what makes atoms stable. If electrons could exist precisely at the nucleus, they'd collapse into it, like marbles falling to the centre of a bowl. But the uncertainty principle forces them to hover at a distance, never still, never perfectly fixed, creating the delicate balance that keeps matter intact. You could say that everything solid owes its solidity to this built-in fuzziness. It's an odd comfort, isn't it? That the walls, the ground, the air all hold together not because they're exact, but because they're uncertain. Einstein once grumbled, "God does not play dice with the universe." But quantum mechanics politely disagreed. The rules of probability aren't chaos. They're the quiet rhythm behind order. Nature rolls its dice with astonishing consistency. Every time, hydrogen glows the same crimson, neon shines the same orange, and sodium lamps give that familiar yellow hue, because each atom's dice are weighted by the precise mathematics of quantum law. And so, beneath the visible world, a subtler one hums, structured not by smooth certainty but by discrete notes of possibility. If you could shrink yourself down to the size of an atom, you wouldn't see particles orbiting like planets. You'd drift through vibrating clouds of presence, each pulse corresponding to a quantized level of energy. This quantization, energy in packets, electrons in defined states, is what gives chemistry its texture. Without it, all colours would blur, all matter would smear, and the concept of bonding would dissolve entirely. Instead, we live in a universe made of steps, not slopes, one that sings in discrete tones. So perhaps the simplest way to think about quantum mechanics is this. Imagine the universe humming softly in a series of notes, each one precise, measured, and full of meaning. The atoms around you are part of that quiet song, every electron vibrating in rhythm with the laws that hold everything together. And in that harmony lies the most wonderful paradox of all, that the deeper we peer into matter, the more it behaves like music. Energy comes in chords, light in scales, and uncertainty in time. Matter, it turns out, isn't merely built, it's composed. If the quantum world had a language, orbitals would be its alphabet. They're not orbits in the planetary sense, no tiny electrons looping around like obedient moons, but mathematical patterns describing where an electron is most likely to be found. Each orbital is a standing wave, a vibration of probability. Instead of sound, they hum with the likelihood of existence. To picture an orbital, imagine plucking a guitar string. The note you hear depends on how the string vibrates, in halves, thirds, or more complex patterns. Now imagine that vibration not along a line, but around an atom in 3 dimensions. Some vibrations form perfect spheres, others stretch out into lobes and loops. These shapes are the visible shadows of invisible equations, and together they build the structure of all matter. The simplest of these shapes is the orbital, calm, symmetrical, and perfectly spherical. It's the quietest vibration an electron can take around a nucleus, a uniform mist of probability where the electron could be anywhere with equal ease. If an atom were a city, this orbital would be the central district, compact, balanced, and always in the same shape no matter how large the atom grows. Move outward and the pattern gains complexity. The next family, the p orbitals, stretch into dumbbell shapes. 2 lobes, one on either side of the nucleus, separated by a thin invisible plane where the probability of finding an electron drops to 0. That empty region is called a node. It's not that the electron refuses to go there, rather, its wave simply cancels itself out. Like 2 ripples on water meeting in perfect opposition, the amplitude falls silent. Beyond that lie the d orbitals, with their elegant 4-lobed symmetries and the even more intricate orbitals, floral, overlapping, and almost too complex to imagine. Together they form the deeper architecture of heavier elements, where electrons begin to occupy these ornate shapes closer to the atom's heart. Each type of orbital, S, P, D, and F, carries its own symmetry, its own capacity, and its own distinct energy. Physicists label these states with 3 quiet numbers, called quantum numbers. The first, n, describes the overall energy level, how far the orbital sits from the nucleus. The second, L, tells us the shape, whether it's spherical, dumbbell-like, or something stranger. And the third, M, describes orientation, the direction that shape points in space. To an outsider it may seem abstract, but to chemists, this numbering system is the secret code that explains why the periodic table looks the way it does. Each additional electron fills the next available orbital in this hierarchy, following rules of symmetry and energy. The lowest energy orbitals fill first, the s, then the p2, and so on, stacking neatly like floors in a cosmic apartment building. When one shell fills, another begins above it, farther from the nucleus and higher in energy. This orderly arrangement creates the very rhythm of the periodic table. Why helium is stable, why sodium reacts violently with water, and why neon glows serenely under electricity. You can think of the periodic table as a map of all possible orbital patterns. Each column represents atoms with similar outermost orbitals, giving rise to shared behaviours. Group 1, the alkali metals, all have a single electron perched in a new unfilled s orbital, eager to leap away. Group 18, the noble gases, have their outermost orbitals completely filled, calm and content, unlikely to react. The table, that grid you may once have memorized in school, is in truth an elegant summary of how probability clouds stack in three-dimensional space. Within these clouds, patterns emerge that shape the geometry of molecules. When atoms bond, their orbitals do not simply sit side by side, they blend. This blending, called hybridization, creates new shapes that fit together more neatly, minimizing repulsion and maximizing stability. Take carbon, the master architect of life. A single carbon atom starts with one s orbital and 3 p orbitals. When it forms bonds, these orbitals mix into 4 equivalent hybrids, the famous sp3 configuration. The result is a tetrahedral shape, like the corners of a pyramid, with bonds pointing as far apart as possible. This symmetry is why methane, CH4, is perfectly balanced in all directions, a miniature geometric sculpture of simplicity. In other molecules the mix changes. In ethene, or C2H4, carbon uses only 3 hybrid orbitals, sp2, leaving one pure p orbital free to form a double bond. The result is a flat planar molecule, its bonds rigid, its shape perfectly defined. For molecules like acetylene, sp hybridization stretches geometry into a straight line, producing the tight triple bonds that store tremendous energy. Through this dance of blending and bending, chemistry gains its variety. Every material, from diamond to graphite, from alcohol to DNA, is sculpted by the quiet cooperation of orbitals finding balance. Nodes, those empty regions where the wave cancels out, are also part of the story. The higher the energy of an orbital, the more nodes it contains. You can think of these as internal boundaries, the mathematical pauses between pulses. The more nodes, the more complex the shape, and the more energetic the electron must be to maintain it. This is why outer electrons sit farther from the nucleus. They occupy orbitals with more nodes, their probability clouds stretched and refined like higher harmonics on a vibrating string. It's remarkable that these invisible structures, derived purely from mathematics, so precisely match reality. When scientists probe atoms using light or scatter electrons through gases, the data reflect exactly these predicted patterns. The equations work because nature truly behaves this way, not with solid surfaces or miniature particles, but with gentle clouds of possibility, governed by symmetry and energy. Electrons, for all their importance, are shy things. They don't like to share the same space or state, yet they prefer to stay close enough to feel one another's presence. In that sense, they're a bit like people at a quiet gathering. Sociable, but only up to a point. It's this push and pull, this balance between attraction and avoidance, that creates all the textures of matter. You could say electrons prefer personal space. They're social but antisocial. The idea that shapes like these, abstract, mathematical and unseen, determine the colour of a gemstone, the smell of a flower, or the flexibility of a metal is both humbling and beautiful. Every chemical property we observe, every reaction we harness, is built upon these standing waves of probability, humming around atomic centers in perfect rhythm. So the next time you look at something as ordinary as a drop of water or a piece of glass, imagine beneath it an intricate world of overlapping clouds, of orbitals interlaced like woven threads. Each atom's electrons are not spinning in circles but vibrating in quiet patterns, perfectly tuned to one another. Every element, every property, every colour and crystal and spark of life begins with these silent shapes in space, the quantum architecture of everything. Deep within the haze of orbitals and energy levels, there is another quiet rule shaping the entire universe, a rule that decides how every atom is built, how every element behaves, and even why magnets stick to your refrigerator. It begins with a curious property called spin. Despite its name, spin isn't really about rotation. An electron isn't a tiny ball whirling in space. It's more like a quantum coin that carries a built-in sense of orientation. Each electron has an intrinsic angular momentum, an internal twist that can be thought of as spin up or spin down. It's not something we can picture directly, but it behaves as if each electron has a tiny magnetic field of its own. This small detail, this whisper of polarity, turns out to be one of the great organizing forces of matter. In 1925, two young physicists, Wolfgang Pauli and George Uhlenbeck, realized that electrons couldn't all pile into the same orbital the way raindrops fall into a puddle. There was a hidden exclusivity at play. Pauli formalized it into what is now called the Pauli exclusion principle. No two electrons in an atom can share the same set of quantum numbers. In other words, each electron must be unique in its address, energy level, shape, orientation, and spin. This rule might sound simple, but it's the reason atoms don't collapse into chaos. Because every orbital can host only two electrons, and only if their spins are opposite, atoms gain a quiet orderliness. Picture an orbital as a small apartment that comfortably fits two tenants, but only if one spins clockwise and the other counterclockwise. Any attempt to squeeze in a third is politely refused by the laws of physics. When you scale this across all the atoms in existence, the result is astonishing. The exclusion principle dictates the entire periodic table. It sets the stage for chemical behavior, defining which elements are stable, which are reactive, and which form dazzlingly complex molecules. It is the universe's seating plan, strict, elegant, and surprisingly consistent. Yet even with these rules, electrons prefer to spread out when they can. This is captured by another principle, called Hund's rule. When multiple orbitals of the same energy are available, electrons fill them singly before pairing up, like passengers on a train choosing empty seats before sitting next to someone. It's not shyness, it's energy efficiency. Keeping spins parallel reduces repulsion and keeps the system calm. Only when every seat is taken do the electrons begin to share. This simple preference explains why some atoms end up with unpaired electrons, and those unpaired electrons are what make materials magnetic. When spins are unbalanced, the tiny magnetic fields of individual electrons fail to cancel, creating a net magnetic moment. In elements such as oxygen or iron, those moments add up, producing paramagnetism or, in stronger cases, ferromagnetism. The next time you see a magnet snap onto metal, you're witnessing the grand alignment of countless unpaired spins, microscopic compass needles all pointing the same way. Oxygen, for instance, offers a perfect example. In its molecular form, O2 has two unpaired electrons, which is why liquid oxygen, though pale blue and seemingly delicate, is actually attracted to magnetic fields. It's a quiet confirmation of the quantum rules written deep inside every atom. The arrangement of electrons, guided by spin and exclusion, also explains the great trends that run across the periodic table. Move from left to right across a period, and each atom gains one more proton and one more electron. The added charge in the nucleus pulls the electrons slightly closer, while the outer shell fills steadily. As a result, atomic size decreases across a row. Go down a group and the opposite happens. New energy levels appear farther from the nucleus, making atoms larger and their outer electrons easier to remove. Ionization energy, the effort required to pull an electron free, follows naturally. Smaller atoms with tightly held electrons like helium or neon demand enormous energy to part with even one. Larger atoms, such as sodium or potassium, release theirs with little resistance. It's why sodium practically leaps into reaction with water, while neon sits aloof, glowing contentedly in signs and never bonding with anything. Then there's electronegativity, a measure of how greedily an atom attracts electrons in a bond. Fluorine, small and fiercely charged, tops the list. Its nucleus pulls shared electrons close, creating highly polar bonds. Metals, on the other hand, with their looser grip, prefer to donate electrons and form positive ions. These patterns, ionization energy rising, atomic size shrinking, electronegativity climbing across a row, are not arbitrary quirks of chemistry. They're the echo of quantum structure, the melody played by the exclusion principle, and the rhythm of electron spin. When Dmitri Mendeleev arranged the periodic table in 1869, he didn't know these quantum rules. He built his masterpiece from observation and intuition, lining up elements by mass and chemical behavior. The beauty is that his chart worked, and decades later, quantum mechanics revealed why. The table wasn't just a catalogue of substances, it was a map of quantum architecture. Each row, each column, each recurring pattern of reactivity arises directly from how electrons fill orbitals under the constraints of spin and exclusion. Take the noble gases along the far right edge. Their orbitals are completely filled. No unpaired electrons, no unfinished business. The result is chemical serenity. They neither give nor take electrons easily, glowing softly when excited but rarely reacting. Contrast that with the alkali metals on the far left, which have a single electron in a new, lonely orbital. That one electron is so weakly bound that it leaps away at the slightest provocation. It's why sodium fizzes, potassium flashes, and cesium practically explodes on contact with water. All of this, from fireworks to magnets to the structure of DNA, emerges from the simple insistence that no two electrons can share the same set of quantum identifiers. The exclusion principle and electron spin are the silent bureaucrats of the cosmos, keeping everything in order, ensuring no two particles ever sit in identical seats. Without them, the universe would collapse into a featureless blob of indistinguishable matter. With them, it blossoms into the diversity of elements and the intricate chemistry of life. It's humbling to think that the patterns you once saw on a classroom wall, that colourful chart of boxes and symbols, is actually a quantum diagram in disguise. The periodic table is a portrait of how electrons arrange themselves, how they compromise between attraction and repulsion, how they obey invisible rules to create visible order. The next time you glance at it, imagine each box not as a simple label, but as a snapshot of an atomic skyline, a set of orbitals filled with spinning electrons, balanced in motion, guided by symmetry. Every element is a unique arrangement of these quantum residents stacked neatly according to the oldest law in physics. Nothing identical may share the same space, and perhaps there's a kind of comfort in that. The universe, for all its vastness, follows a set of quiet principles: spin, exclusion, and balance. Together they create everything from the hardness of diamond to the oxygen in your lungs. The seating plan of existence may be strict, but is also beautifully fair. At the heart of chemistry lies a quiet act of sharing. Two atoms drifting close enough for their electron clouds to touch find a kind of balance, neither fully giving nor fully taking, but overlapping just enough to create something new. That shared region of space, where the electrons belong to both atoms at once, is the simplest possible bond. It is the beginning of a molecule, and for hydrogen, it is the most fundamental partnership in the universe. When two hydrogen atoms meet, each brings one electron in its tiny s orbital. As they approach, those orbitals begin to overlap, and the electrons find a shared rhythm. Their opposite spins align into a pair, lowering the total energy of the system. In that moment of cooperation, the hydrogen molecule, H2, is born. The electron density now sits between the two nuclei, like a soft cushion of charge holding them together. It's not a physical string, but an invisible region of probability that glues the atoms in place. This way of looking at bonding is called valence bond theory, and it paints an intuitive picture. Orbitals overlap like interlocking waves, creating new shapes where electrons can exist simultaneously near both nuclei. These shared pairs are what chemists call sigma bonds, the simplest and strongest type, concentrated directly along the line connecting the two atoms. When orbitals overlap side by side instead of head-on, they form pi bonds, slightly weaker but still vital. Together, sigma and pi bonds make up the backbone of molecules, from the hydrogen in the air to the carbon chains that make up life. Valence bond theory also explains why molecules have shapes. When orbitals mix or hybridize, they create geometries that minimize repulsion between electron pairs. A carbon atom, for instance, begins with one s orbital and three p orbitals. These combine into four equal hybrids, sp3 orbitals, that point toward the corners of a tetrahedron. The result is a perfectly symmetrical shape, found in methane, CH4, where each hydrogen is held at equal distance from the center. The molecule's balance is not accidental. It's written into the mathematics of overlapping waves. When one of those bonds becomes a double bond, as in ethene, the carbon atoms use three hybrid orbitals each, sp2, arranged in a flat triangular plane. The leftover unhybridized p orbitals on each carbon overlap sideways to form the extra pi bond. It's what locks ethene into its planar shape, making rotation around the bond nearly impossible. In the case of acetylene, or ethene, the carbon atoms go even further, using two hybrid orbitals, sp, forming a straight line. The two unhybridized p orbitals create two pi bonds, giving acetylene its famously strong triple bond. Valence bond theory tells a beautiful story of bonds as localized partnerships, two atoms, two orbitals, and one shared region of electron density. But it isn't the only way to describe this dance. To see the bigger picture, chemists turn to molecular orbital theory, a view where electrons are not confined between specific atoms, but spread across the entire molecule like delocalized waves. In this approach, when two atomic orbitals combine, they form not one but two new molecular orbitals, a bonding orbital and an anti-bonding orbital. In the bonding orbital, the waves from each atom reinforce one another between the nuclei, increasing electron density where it holds the atoms together. In the anti-bonding orbital, the waves cancel out, leaving a node, a region of zero electron probability between the atoms. Occupying the bonding orbital lowers energy, while occupying the anti-bonding one raises it. Hydrogen, once again, offers the simplest example. When two hydrogen 1s orbitals overlap, they create one bonding and one anti-bonding orbital. The two electrons both occupy the lower bonding orbital, producing a stable H2 molecule. Add a third electron, as in a hypothetical H2- ion, and it begins to destabilize. Add a fourth, as in helium, and the balance flips entirely. Each helium atom contributes 2 electrons. Together they fill both the bonding and anti-bonding orbitals, cancelling the stabilization out. The result? He too cannot exist. The molecule simply falls apart. That contrast, hydrogen stable, helium unstable, demonstrates how the filling of molecular orbitals determines whether a bond will form at all. Chemistry, it seems, is as much about subtraction as addition. Molecular orbital theory also explains phenomena that the localized valence bond model struggles with. Oxygen, for example, is famously magnetic, a fact that puzzled chemists for years. In valence bond terms, all of oxygen's electrons appear neatly paired, but experiments showed that liquid oxygen is attracted to magnets, implying unpaired spins. Molecular orbital diagrams solved the mystery. The two highest energy orbitals in O2 are antibonding pi orbitals, each occupied by a single unpaired electron. These unpaired spins give oxygen its paramagnetism, and the model matches the observation perfectly. Another powerful idea from molecular orbital theory is delocalization. Electrons spreading across multiple atoms rather than staying between just two. In molecules like benzene, a ring of 6 carbon atoms, the electrons in the pi orbitals aren't tied to individual bonds. Instead, they form a continuous cloud circling the ring, evenly distributed. This delocalization gives benzene its remarkable stability and unique chemistry. It's as if the electrons have agreed to share ownership of the entire molecule, resulting in a resonance that no single Lewis structure can fully capture. These delocalized molecular orbitals appear everywhere in chemistry, in the colors of dyes, the conductivity of metals, the reactivity of enzymes. They even determine how substances interact with light. The energy gap between the highest occupied molecular orbital, the HOMO, and the lowest unoccupied one, the LUMO, dictates how much energy is needed to excite an electron, and thus what color of light it absorbs. A small gap means lower energy absorption and deeper colors, a larger gap, higher energy and paler tones. The brilliant hues of pigments, the glow of LEDs, even the way leaves appear green all trace back to differences in molecular orbital spacing. So in a sense, valence bond theory and molecular orbital theory are two perspectives on the same phenomenon, the local and the global, the duet and the orchestra. Valence bond theory captures the intimacy of a single shared pair, like two dancers moving in step. Molecular orbital theory shows the choreography from above, the patterns and harmonies that emerge when many electrons move together. It's tempting to ask which one is right, but the truth is that both are. Each model illuminates a different aspect of bonding, and chemists move between them as naturally as switching between languages. Together, they describe how atoms, built on quantum uncertainty, manage to form the predictable structures we depend on. Every stable material, from the air we breathe to the steel in bridges, is born of these overlapping clouds. Electrons pooled into quiet partnerships, sometimes between two atoms, sometimes shared among many. What we call matter is really the geometry of probability, stitched together by the balance of attraction and repulsion, node and overlap. If you could see a molecule not as sticks and spheres but as shimmering waves, you'd witness something astonishing. A blur of patterns, peaks of density where electrons prefer to be, soft gaps where they do not. Bonds would appear not as lines but as glowing threads of shared uncertainty. And in that view, chemistry reveals its true poetry. Valence bond theory tells you who's dancing, which atoms share their electrons. Molecular orbital theory shows you the choreography, the rhythm, the symmetry, the harmony of the whole. Together they explain how the universe's smallest players create everything from water to sunlight to life itself, one quiet overlap at a time. Every chemical reaction, no matter how simple or complex, is a kind of journey, one that travels through an invisible landscape of energy. The terrain isn't made of hills and valleys of earth, but of potential energy. Every atom, every bond sits at a specific energy level, and when bonds break or new ones form, the path between them can be drawn as a winding trail through this unseen world. Chemists call it a potential energy surface, or PS for short, and though you'll never see it with your eyes, it's one of the most important maps in all of science. Imagine a valley where the reactants begin, a comfortable, stable basin where atoms rest in familiar arrangements. To transform into products, they must climb out of that valley, cross a ridge, and descend into another, slightly different basin. That ridge, the highest point along the lowest possible path, is known as the transition state. It's the peak of the journey, the moment of maximum instability, where bonds are half broken and half formed, and the molecule hovers in delicate balance between what it was and what it will become. The height of that ridge, the energy required to reach it, is the activation energy. It's what determines how quickly a reaction proceeds. The higher the barrier, the slower the process. The lower it is, the faster atoms rearrange themselves. Every reaction you've ever seen, a match flaring to life, a cake browning in the oven, the slow rusting of iron, is governed by this simple geometry of energy. It's an elegant idea, but also a very human one. The molecules are just like us. They prefer low energy, stable situations. They're happy to stay nestled in their valleys unless given a reason to move. To react, they need a push. Heat, light, friction, or even another molecule bumping into them with just the right energy and angle. When they do cross that invisible mountain pass, the energy they gained is released again as they settle into the product valley. Sometimes it comes out as heat, sometimes as light, sometimes stored in new bonds waiting to be released later. A reaction doesn't follow just any random route from one valley to another. It chooses the path of least resistance, the lowest possible climb between the two. You could think of this path as the narrow trail carved by the footsteps of probability, where countless collisions and configurations have worn down a single efficient route through the energy landscape. Even molecules, it seems, prefer the easier road. To make this landscape more tangible, imagine one of the simplest chemical transformations, an SN2 reaction, short for substitution nucleophilic bimolecular. In plain English, one atom or group leaves and another takes its place, both involved in a single simultaneous step. Picture a carbon atom at the centre, bonded to a leaving group, perhaps a chlorine atom, while a new group, maybe a hydroxide ion, approaches from the opposite side. As the incoming nucleophile draws near, the bond to the leaving group begins to stretch, the electron density redistributes, and for a fleeting instant the carbon sits in a five-fold coordination, something it was never meant to do for long. That moment, caught halfway between breaking and forming, is the transition state. It exists for only a few femtoseconds, but it defines the entire reaction's speed. Once that fragile configuration resolves, the leaving group departs, the new bond solidifies, and the system slides smoothly down into a new valley, the product basin. If you could visualize this reaction on a potential energy diagram, it would look like a single smooth hill between two valleys. The starting materials rest on one side, the products on the other, and the peak in the middle represents that unstable transition. The height of the hill determines how hard it is for the reaction to proceed. A lower hill means an easier path, a higher one, a slower transformation. Temperature in this analogy is like the energy of hikers attempting to cross. At higher temperatures, more molecules have enough energy to climb over the barrier, so the reaction speeds up. At lower temperatures, fewer make the ascent, and the process slows to a crawl. This is why food spoils faster in warmth and why refrigerators are chemical time machines, slowing the invisible reactions that cause decay. Now, Some reactions face hills so tall they might as well be mountains. Left alone, they would take centuries to happen. This is where catalysts come in, the trail engineers of chemistry. A catalyst doesn't change where the journey begins or ends. The reactants and products remain the same. Instead, it carves an easier path through the landscape, lowering the activation energy. It may offer a shortcut, a tunnel through the ridge, or even an entirely different route that bypasses the mountain altogether. Enzymes, the biological catalysts inside living cells, are masters of this craft. They shape their active sites like finely tuned landscapes of their own, guiding reactants into perfect orientation, stabilizing transition states, and releasing products with almost effortless grace. Thanks to these molecular sculptors, reactions that would otherwise take years can unfold in milliseconds, allowing life to exist at all. Catalysts in human industry perform similar feats. They turn raw petroleum into fuels, nitrogen and hydrogen into ammonia for fertilizers, and carbon dioxide into useful compounds. Every catalytic process is a reshaping of an energy landscape, a redesign of the terrain to make the climb easier, the descent smoother, and the outcome faster. Chemistry, when you think about it, is never truly still. Even in the most stable material, tiny thermal vibrations ripple through the structure, pushing and pulling, testing the slopes of the potential surface. Every moment, billions of molecules are attempting climbs, many failing, a few succeeding, always seeking that next valley. Some transitions release energy, warming your hands, others absorb it, cooling the air. All follow the same quiet rule. Systems move toward stability, toward lower energy, toward balance. If you could somehow wander across one of these potential energy surfaces, to walk the rolling hills of molecular possibility, you'd find landscapes of staggering complexity. Valleys connect to other valleys through narrow passes, sometimes leading to dead ends, sometimes branching into whole networks of reactions. A molecule doesn't see a single path, but a vast terrain of options. The art of chemistry is finding which route it takes and how to encourage the right one. And yet, amid all this activity, the rule remains beautifully simple. To react is to climb, and to change is to descend. Bonds break at the crest. New ones form on the way down. The hill may be invisible, but every transformation you've ever witnessed follows its contours. So the next time you watch sugar caramelize in a pan, or metal darken with rust, picture this invisible geography. Picture each atom hiking across its own energy terrain, searching for balance on a microscopic scale. The heat you add is their encouragement, their gentle shove toward the summit. And when they finally cross it, when the transition state passes and the bonds realign, energy flows outward as the molecules settle into their new resting place. Every chemical change, from the slow weathering of stone to the flash of an explosion, is a quiet journey through this unseen landscape. The terrain is shaped by quantum rules, yet the story it tells feels almost familiar. There are climbs, descents, barriers, and shortcuts, challenges to overcome and balance to be found. In the end, chemistry is less about chaos and more about guidance. Molecules don't wander blindly. They move according to the contours of energy that guide them, always downhill in the end. Every transformation is a slow walk over an invisible hill, a quiet hike through the geometry of change, written not in rock and soil, but in the language of energy itself. No molecule lives alone. Every atom, every reaction, every flicker of motion happens inside some kind of environment, whether that's a droplet of water, a thin layer of oil, a crowded cell, or the open air. Chemistry never takes place in a vacuum, though it sometimes pretends to on paper. In reality, the space around a molecule matters almost as much as the molecule itself. The solvent, the temperature, the neighbouring ions, All of them shape what happens next. You could say that a molecule's mood depends entirely on the room it's in. The simplest way to picture this is to think about solvents, the background fluid that surrounds reactants and gives chemistry its stage. Solvents aren't passive spectators. They tug, twist, and stabilize the molecules they host. The key quality that decides how they do this is something called polarity, a measure of how unevenly electrical charge is distributed within their molecules. Water, for example, is highly polar. Its oxygen atom holds electrons more tightly than its hydrogens, creating a partial negative charge near the oxygen and a partial positive charge near the hydrogens. This gives each water molecule a tiny dipole moment, like a microscopic magnet. When placed near charged or polar molecules, these water dipoles arrange themselves in response, positives facing negatives, negatives facing positives, wrapping the solute in a flexible, flickering embrace. This behavior is measured by a property called the dielectric constant, which describes how well a material can reduce the strength of electric fields. High dielectric solvents like water can stabilize ions beautifully. They spread out the electric forces, softening attractions and repulsions. Non-polar solvents such as hexane or benzene do not. Their charge distribution is too even, so they can't shield or stabilize charged species effectively. As a result, a salt that dissolves effortlessly in water will stubbornly remain a solid in hexane. This distinction explains why acid-base reactions behave so differently in different environments. In water, acids dissociate easily. The positive hydrogen ion doesn't wander alone. It instantly binds to water molecules, forming the hydronium ion and spreading its charge across several neighbours through hydrogen bonding. Bases too are stabilised by the same network, but in a nonpolar solvent like hexane, there's no such safety net. Charged intermediates are left exposed, their electrostatic energy unbuffered. Reactions that are lightning fast in water may crawl at a glacial pace or fail entirely when moved into a nonpolar medium. Hydrogen bonding plays a special role in this molecular dance. It's not a true bond in the chemical sense, more like an attraction between a partially positive hydrogen and a nearby electronegative atom, such as oxygen or nitrogen. Yet these weak interactions collectively shape the structure of liquids, biological molecules, and even crystals. Water's remarkable properties, its high boiling point, its ability to dissolve so many substances, its expansion upon freezing, all stem from its dense network of hydrogen bonds. They are constantly breaking and reforming, lasting only trillionths of a second each, but together they give water its resilience and complexity. Ionic interactions, on the other hand, dominate in charged environments. When oppositely charged ions meet, they attract strongly, sometimes forming lattices as in salt crystals. In solution, the surrounding solvent molecules compete with this attraction, wedging themselves between the ions and pulling them apart. That's what dissolving really is, a tug-of-war between ionic attraction and solvent stabilization. A polar solvent wins this contest easily, a non-polar one barely participates. When chemists try to simulate such systems with computers, they have to decide how to represent the solvent. One option is to treat it implicitly, as a kind of continuous background that averages out all the solvent's effects into smooth equations. This approach is fast and efficient, good for big systems or when the details of individual solvent molecules aren't critical. The other option is explicit solvation, where each solvent molecule is represented and allowed to move, rotate, and interact directly with the solute. This method is slower, but it reveals subtle effects like specific hydrogen bonds, ion pairing, and the gentle fluctuations that can steer a reaction. Neither approach is universally better. Both are useful depending on what questions are being asked. In quantum chemistry, this balance of detail versus simplicity mirrors a wider truth. The more closely you look, the more complex reality becomes, and the more clever approximations you need to make sense of it. Sometimes chemists need both views at once. That's where the QMMM approach comes in, short for quantum mechanics and molecular mechanics. In this hybrid method, the part of the system that truly requires quantum precision, such as a reacting molecule or an enzyme's active site, is treated using quantum mechanics. The rest, the surrounding solvent, the protein structure, the distant atoms, is modelled using classical physics. It's like zooming in on the musicians playing the solo while keeping the rest of the orchestra in the background. You capture the crucial detail without wasting energy, modelling every note from every instrument. This kind of modelling has transformed modern chemistry and biology. It allows scientists to understand how enzymes fold around molecules, how drugs bind to receptors, and how subtle changes in solvent composition can alter entire reaction mechanisms. In drug design, for example, knowing how water molecules arrange around a potential medicine can make the difference between a life-saving drug and one that never works. Solvent interactions influence how well a compound dissolves, how it finds its target, and how tightly it binds when it gets there. In environmental chemistry, solvents determine how pollutants move through ecosystems, whether they dissolve in rainwater and spread, or cling to fats and linger in living tissues. Understanding solvent effects helps scientists predict which substances will disperse harmlessly and which will persist for decades. The invisible chemistry of the surroundings becomes, quite literally, the fate of the planet. It's remarkable how much personality solvents give to reactions. Water is the lively social type, constantly forming and breaking connections, keeping everything mobile and reactive. Hexane, by contrast, is solitary and detached, allowing molecules to keep their distance. Alcohols are somewhere in between, capable of both dissolving and interacting. The solvent doesn't just hold the reaction, it shapes its tone. And yes, even molecules seem to crave comfort. Some reactions thrive in crowded polar environments, surrounded by stabilizing neighbors. Others prefer the quiet emptiness of a non-polar space, free from interference. You could almost imagine the molecules sighing in relief when they find the right surroundings. Even molecules, after all, need a comfortable atmosphere. If you zoomed out and looked at all of chemistry through this lens, you'd see a universe of interactions, not just between atoms, but between matter and its context. Solvents and surroundings are the stage, the lighting, the air temperature, and even the audience's mood. A reaction that looks predictable in theory may act completely differently in the real world, simply because the environment whispers a different instruction. So, when thinking about chemistry, it helps to remember that molecules never perform in isolation. They're part of a larger scene, a molecular theatre where the background is as active as the actors. Water, oil, air, and everything in between are silent participants in every chemical story. In the end, chemistry is not just about what happens, but where it happens. Change the surroundings and you change the story. A molecule's reactivity, colour, and even its very stability depend on the company it keeps. The solvent isn't just the background, it's the mood, the atmosphere, the uncredited character that decides how the plot unfolds. If chemical reactions could speak, most would admit they can be rather lazy. They know where they want to go, from reactants to products, but often the path is steep and exhausting. To get there, they need help. That help comes in the form of catalysts, the silent architects of the molecular world. They don't take part in the final product, they aren't consumed by the process, yet they change everything. Their magic lies in simplicity. They make the same transformation happen faster, more efficiently, and often under gentler conditions. At its heart, catalysis is about lowering the barrier. Remember the invisible hills and valleys of reaction landscapes? A catalyst doesn't change where those valleys lie. The energy of the starting materials and the product stays the same, but it smooths the climb between them. It offers a shortcut over the mountain pass or digs a tunnel straight through it. The overall destination is unchanged, but the journey becomes far easier. What makes this so remarkable is that the catalyst itself remains intact at the end of the process. It might temporarily form bonds, stabilize an intermediate, or shuttle electrons between reactants, but by the time the product's released, the catalyst has quietly reset itself, ready for another round. It is, in a sense, the ultimate multitasker, doing enormous work while appearing to do nothing at all. Catalysts come in many forms, but chemists often group them into two broad families, homogeneous and heterogeneous. The first, homogeneous catalysts, share the same phase as the reactants, usually existing together in a liquid solution. They mingle freely, able to interact on the molecular level with precision. These are the maestros of fine-tuned chemistry, orchestrating specific transformations with elegant control. Heterogeneous catalysts, by contrast, stand apart, usually solid surfaces interacting with gaseous or liquid reactants. They work more like sturdy workbenches. Reactions happen on their surfaces at the precise spots where atoms are bound and released. Though they may not mingle with the molecules, they provide structure, guidance, and stability, a place for chemistry to happen efficiently. One of the most familiar examples of heterogeneous catalysis is found in catalytic converters, the unsung heroes of your car's exhaust system. Hidden beneath a layer of metal and ceramic, these catalysts, made from precious metals like platinum, palladium, and rhodium, quietly transform toxic gases into harmless ones. Carbon monoxide, nitrogen oxides, and unburned hydrocarbons pass over their surfaces and are rearranged into carbon dioxide, nitrogen, and water vapor. Billions of reactions happen every second, all guided by the catalyst's steady hand. Without it, every drive would be a miniature environmental disaster. Another famous catalyst has had an even greater impact on human history, the one behind the Haber-Bosch process. In the early 1900s, Fritz Haber and Carl Bosch developed a method to synthesize ammonia by combining nitrogen from the air with hydrogen gas. The reaction itself is simple to describe, but ferociously difficult to perform. Nitrogen molecules are held together by one of the strongest bonds in chemistry. Breaking it requires immense energy. The catalyst, made from iron with small amounts of potassium and aluminum oxides, weakens that stubborn nitrogen bond just enough to let the reaction proceed under manageable conditions. The ammonia produced by this process became the foundation for fertilizers that feed much of the world. It's estimated that half of the nitrogen atoms in your body, in your muscles, your DNA, your very being, once passed through a Haber-Bosch reactor. A single catalytic idea reshaped civilization, turning the air itself into food. Few inventions can claim such quiet power. Nature, of course, was using catalysts long before humans gave them a name. Enzymes, the biological catalysts that drive life's chemistry, are masterpieces of molecular engineering. Each enzyme is a folded protein whose shape is perfectly tailored to a particular reaction. Inside the enzyme's active site, atoms are positioned with exquisite precision, aligning orbitals just so, stabilizing fleeting intermediates, and creating the perfect environment for transformation. In enzymes, catalysis becomes almost an art form. Some use metal ions to shift charges. Others rely on amino acid residues to transfer protons or form temporary bonds. Many achieve their speed through sheer geometry, by holding reactants in exactly the right orientation. The effect is staggering. An enzyme can accelerate a reaction by factors of millions or even billions. A process that would take centuries in a test tube can unfold in milliseconds inside your cells. Take carbonic anhydrase, for example, an enzyme that helps regulate carbon dioxide in your blood. Without it, the removal of carbon dioxide from tissues would be painfully slow. With it, the reaction proceeds at lightning speed, keeping every breath you take in perfect balance. Or consider DNA polymerase, which copies genetic material with accuracy and speed that no machine could match. Every heartbeat, every spark of thought depends on catalytic precision honed by billions of years of evolution. What all catalysts, biological or synthetic, have in common is their mastery of orbital alignment. Chemical reactions happen when orbitals overlap correctly, when electrons can flow smoothly from one atom to another. Catalysts excel at arranging these encounters. They hold reactants in the right orientation, polarize bonds to make them easier to break, and stabilize transition states so that the climb up the energy hill is less steep. Sometimes they even provide temporary bonding partners, creating intermediates that wouldn't exist otherwise. If you were to watch catalysis at the quantum level, it would look like a perfectly choreographed dance. The reactants approach, guided by the catalyst structure. A bond stretches, another forms, and just as instability peaks, the catalyst steps back, leaving the products to fall into their new, lower energy configuration. Then the dance begins again, billions of times per second, tirelessly, without complaint. Modern chemistry is now extending the concept even further. Researchers are developing green catalysts, designed to make reactions cleaner and more sustainable. Traditional industrial catalysts often rely on rare or toxic metals, but new generations of catalysts use abundant elements like iron, nickel, or even carbon-based frameworks. Others operate in water instead of harmful solvents, or at lower temperatures, saving energy and reducing waste. These innovations follow the same timeless rule: find a smoother path, one that works with nature rather than against it. Catalysts also play a crucial role in emerging fields like renewable energy. They split water into hydrogen and oxygen in fuel cells, help store energy in chemical bonds, and convert carbon dioxide back into useful fuels. The dream of a sustainable energy cycle depends as much on clever catalysis as on sunlight or wind. If energy is the heartbeat of civilization, catalysts are the arteries, the pathways that make it flow. It's fascinating to realize that, on some level, everything alive and everything built relies on catalysts. From the enzymes digesting your dinner to the metals purifying the air outside, they're constantly working behind the scenes. They ask for nothing, they change nothing of themselves, and yet without them, the world would move unbearably slowly. So perhaps it's fair to call catalysts the unsung heroes of chemistry, speeding up the world politely. They make no noise, demand no attention, but they are everywhere, in our engines, our industries, our cells. Progress, in chemistry as in life, is rarely about forcing change. More often, it's about finding smoother paths, lowering the barriers, and letting nature take its easiest route. Catalysts simply show the way, and then quietly they step aside. If you could shrink down far enough to stand among the atoms of a molecule, you wouldn't find stillness. You'd find rhythm. Every bond, every atom, every stretch of matter vibrates, twists and bends in a microscopic dance. Molecules are never truly at rest. Even at absolute zero, they tremble faintly, whispering in quantized tones. Each vibration corresponds to a specific energy, and together they form a kind of molecular symphony. This isn't poetry, it's physics. Every vibration within a molecule occurs in discrete steps, never in between. When a bond stretches, it can only do so by exact amounts of energy. like the strings of a violin that can play distinct notes but nothing in between them. These vibrations can be stretching motions, where atoms pull apart and snap back like tiny springs, or bending motions, where bonds angle in and out, twisting and swaying in precise rhythm. Each mode has its own frequency, its own pitch, defined by the strength of the bond and the mass of the atoms. When light encounters these vibrating molecules, something wonderful happens. The two can communicate. Light can give or take exactly the right amount of energy to move a molecule from one vibrational level to another, and by studying which wavelengths of light are absorbed or scattered, chemists can listen to these invisible songs. That is the essence of spectroscopy, the science of hearing what molecules have to say. Infrared spectroscopy is one of the most elegant ways to do it. Infrared light carries just the right amount of energy to match molecular vibrations. When a molecule absorbs an infrared photon, one of its bonds begins to oscillate faster, stretching a little further, bending a little wider. Each type of bond responds to a specific wavelength, producing a spectrum of absorption peaks that form a kind of barcode unique to that molecule. This is how scientists can identify substances with extraordinary precision. The carbonyl bond in a ketone, for example, vibrates strongly around 1700 reciprocal centimeters, producing a sharp, distinctive peak. Hydroxyl groups sing at a different frequency, and carbon-hydrogen bonds have their own subtle harmonics. Put them all together, and you have the fingerprint of a molecule, a spectral signature that no other structure shares. You've never truly heard music until you've heard a carbonyl stretch. A related but subtly different technique is Raman spectroscopy. Instead of absorbing light, the molecule scatters it, sending it back out at slightly different energies. Most light scatters elastically, meaning it bounces back unchanged. But a tiny fraction interacts with the molecule's vibrations, emerging shifted in frequency, either a little higher or a little lower, depending on whether energy was gained or lost. Measuring these shifts gives another window into the molecule's vibrational modes. Raman spectroscopy is like listening to echoes rather than direct notes. It complements infrared beautifully. Some vibrations that are silent in infrared sing loudly in Raman, and vice versa. Together they provide a complete score of molecular motion, a duet between absorption and scattering. Move higher in energy, and we reach ultraviolet visible spectroscopy, or UV-vis for short. Here, the light is powerful enough to promote electrons between energy levels, rather than simply make bonds vibrate. When a photon of the right energy strikes a molecule, it can push an electron from a lower orbital to a higher one, temporarily exciting it. The energy difference between these orbitals determines which wavelength of light is absorbed, and the remainder is what we perceive as colour. Pigments, dyes, and even the colours of plants and minerals owe their hues to this quantum exchange. Chlorophyll absorbs red and blue light, reflecting green. Carotenoids soak up blue light and shine with the warm tones of autumn. Transition metals with their rich D and F orbitals produce vibrant blues and reds in crystals and glass. Every shade of nature's palette is a record of electronic transitions, the quantum version of brush strokes. Then there's nuclear magnetic resonance, or an MR spectroscopy, a slower, more methodical melody. Here it's not electrons or vibrations that sing, but atomic nuclei themselves. Certain nuclei, like hydrogen and carbon-13, possess their own spin, behaving like tiny magnets. When placed in a strong external magnetic field, these nuclear magnets align either with or against the field, creating two distinct energy states. By pulsing the sample with radio waves, chemists can flip those spins between states, and when they relax back, the nuclei emit signals that reveal their environment. Each nucleus feels a slightly different magnetic field depending on the nearby electrons and atoms, producing a spectrum of peaks that can be decoded to reconstruct entire molecular structures. It's as if every atom whispers its postal address, and from the collection of voices the full neighbourhood is revealed. NMR is especially beloved in organic chemistry and biochemistry because it gives direct, almost intimate information about structure. You can use it to determine how atoms are connected, how they move, and even how proteins fold. It's slow compared to infrared or UV vis, but it tells stories that no other method can. Stories of proximity, symmetry, and motion. And then, at the highest energies, there is X-ray diffraction, a technique that doesn't listen to vibrations or spins but maps the very shape of matter. When X-rays pass through a crystal, the tightly packed atoms scatter the radiation in precise directions, producing a pattern of bright spots. By analysing those patterns, scientists can reconstruct the three-dimensional arrangement of atoms inside the crystal. It was through X-ray diffraction that Rosalind Franklin revealed the helical structure of DNA, and countless other molecular architectures have since been unveiled in the same way. Each of these techniques is, in its own sense, a form of listening. Infrared hears the hum of bonds stretching and bending. Raman catches the scattered echoes of that same melody. UV vis perceives the flash of electrons leaping between orbitals. NMR hears the soft spin of nuclei turning in magnetic rhythm, and X-ray diffraction, though silent, shows the stage itself, the fixed positions where all those motions begin. Together they form a complete orchestra of molecular expression. To a spectroscopist, the world is full of music, solids, liquids, gases. Everything vibrates, scatters, absorbs, and emits in perfect quantized harmony. The instruments are invisible, but the notes are unmistakable, each one governed by the same underlying mathematics that describes waves and energy. Spectroscopy doesn't just satisfy curiosity, it has shaped the modern world. Infrared and Raman spectroscopy identify unknown compounds in forensics and pharmaceuticals. UV vis analysis measures pollution in air and water, detects impurities in materials, and even monitors reactions in real time. NMR spectroscopy helps design new drugs, study proteins, and understand metabolism. And X-ray diffraction underpins the fields of crystallography, materials science, and molecular biology. We also use these techniques to explore beyond our planet. When light from distant stars passes through planetary atmospheres, their unique spectral fingerprints reveal what elements and molecules are present. That's how we know about methane on Mars, water on exoplanets, and organic compounds drifting through interstellar clouds. The same physics that helps identify a mystery compound in a lab also lets us read the chemistry of entire worlds. It's poetic that from the quantum hum of a single molecule, we can infer the composition of the cosmos. Every vibration, every transition, every diffraction pattern is part of a universal language of light and matter. To understand it is to eavesdrop on the workings of the universe itself. So perhaps chemistry's most beautiful truth is that matter does not sit silently. It sings. Each molecule has its own song, its own rhythm of motion and light. And spectroscopy, in all its forms, is the art of listening. Next time you see a colour, feel warmth, or smell something in the air, remember, what you sense is the music of molecules, playing softly in the background of existence. Light is more than something we see, it's something matter feels. Every beam of sunlight, every flicker of a lamp is made of countless tiny messengers called photons, packets of energy moving through space at the ultimate speed limit. When these photons meet matter, they don't always bounce or pass through. Sometimes, if their energy is just right, they're absorbed, and in that instant, an electron inside the atom or molecule leaps to a higher energy state. These leaps are what make chemistry shimmer, glow, and react. Each one is quantized, meaning the photon must carry exactly the right amount of energy to bridge the gap between the electron's current level and the next available one. Too little and nothing happens. Too much and the photon passes by unacknowledged. It's like tossing pebbles at a window. Only one of a precise size and speed will make the perfect sound. These specific transitions give rise to everything from the colours of objects to the reactions that power photosynthesis. When light is absorbed, an electron briefly moves to an excited state, a higher energy orbital. But nature prefers efficiency, and the electron soon finds its way back home, releasing the excess energy in some form, as light, as heat, or sometimes as chemical change. Not all transitions are created equal, however. Quantum mechanics enforces a set of elegant rules called selection rules that govern which energy jumps are allowed and which are forbidden. They're not moral judgments, just mathematical constraints based on symmetry and conservation of angular momentum. In simple terms, certain transitions require the electron's wave function to change shape or orientation in very specific ways. If the symmetry of the molecule or the orbitals doesn't permit it, the transition can't happen easily. This is why some materials glow brightly while others stay dark, even under the same light. Allowed transitions happen quickly, efficiently. The electrons jump, fall back, and radiate energy in a blink of an eye. Forbidden transitions, on the other hand, still occur, but much more slowly. It's the universe's way of whispering, "You can do this, but only if you're patient." This distinction lies at the heart of fluorescence and phosphorescence, two of chemistry's most captivating light tricks. In fluorescence, an electron absorbs a photon and quickly drops back to its ground state, releasing a new photon almost instantly, usually within a few billionths of a second. The emitted light is lower in energy than the absorbed light, which is why fluorescent materials often glow in bright colours after exposure to ultraviolet light. Phosphorescence is slower and more mysterious. It happens when the excited electron slips into a state with a different spin configuration, something that breaks the normal symmetry rules. Because this transition back to the ground state is forbidden, the electron lingers in limbo, sometimes for seconds or even hours. When it finally releases its energy, we see that ghostly afterglow, the gentle green shimmer of glow-in-the-dark paint, the fading sparkle of certain minerals. It's as though the molecule took a deep breath and exhaled its light long after the world moved on. Light interacts with more than just isolated atoms. It weaves colour into the very fabric of molecules. In organic compounds, extended chains of alternating single and double bonds, known as conjugated systems, create regions where electrons can move freely across multiple atoms. These delocalized electrons form molecular orbitals that are closer in energy, allowing visible light to promote transitions between them. The longer the conjugated system, the smaller the energy gap and the redder the absorbed light appears. This is why small molecules absorb only ultraviolet light and remain colourless, while larger conjugated molecules, like carotenoids in carrots or chlorophyll in leaves, absorb in the visible range. Chlorophyll, with its ring of conjugated bonds surrounding a magnesium ion, soaks up red and blue wavelengths and reflects green, painting the living world with its familiar hue. Carotenoids absorb blue light, leaving behind their warm oranges and yellows. The chemistry of colour is, in truth, the physics of electrons dancing to light's tune. Even the artificial colours of modern life follow the same rule. The brilliant shades of car paint, the glow of neon signs, the rich tones of textile dyes, all emerge from carefully designed conjugated molecules tuned so their electronic transitions fall within the visible spectrum. A tiny adjustment to the molecular structure, An extra double bond here, a change of atom there, can shift a colour from crimson to violet. Artists, chemists, and quantum mechanics share more common ground than one might think. In the realm of metals, light and matter take on yet another dimension. Metal atoms contain many closely spaced d orbitals, and when these orbitals interact with surrounding ligands, molecules or ions bound to the metal, they split in energy. This splitting, known as the ligand field effect, determines which wavelengths of light are absorbed, and thus what colour the complex appears. Cobalt complexes, for instance, can appear deep blue or pink depending on the ligands around the metal. The colours are a direct expression of quantum mechanics. The photons being absorbed correspond precisely to the energy gap between split d orbitals. The same principles govern the vivid reds of ruby and the greens of emerald, both forms of aluminum oxide coloured only by traces of chromium atoms whose d orbitals absorb specific frequencies of light. Even gemstones, it turns out, are miniature quantum experiments frozen in stone. These same interactions are put to work in countless modern technologies. Light-emitting diodes, or LEDs, create light through controlled electron transitions in semiconductors. When an electron in the material recombines with a positively charged hole, the energy released is emitted as a photon. By carefully engineering the semiconductor's band gap, manufacturers can produce any colour of light, from the deep blues of phone screens to the warm whites of bedside lamps. Lasers, too, rely on light-matter interaction, but in a more disciplined way. Inside a laser cavity, atoms or molecules are excited into specific states, then stimulated to release photons that are all identical, same energy, same phase, same direction. The result is a perfectly coherent beam of light, focused enough to cut metal, or, with gentler wavelengths, read data from a disc or repair tissue in the human eye. What began as an exploration of quantum transitions has become one of the most versatile tools in science and industry. Even our own eyes are quantum detectors. The pigments in our retinas, tiny conjugated molecules called retinal, undergo a subtle electronic transition when struck by light, changing shape and triggering the nerve signals that create vision. Every colour, every shade, every glimmer of the world around you begins with a photon's delicate nudge against an electron. The interplay of light and matter reaches across every scale of existence. It drives photosynthesis, powers solar panels, colours the sky, and fills the night with both artificial and natural glow. It links the microscopic with the cosmic. The same photon that excites a molecule of chlorophyll might, given time, travel across space to be absorbed by dust surrounding a distant star. Light doesn't just reveal chemistry, it conducts it. Every photon is a note in the universal score, carrying energy from one place to another, setting electrons into motion, creating colour, warmth, and life itself. If molecules are the instruments of the universe, then light is the musician, forever playing the quiet, intricate symphony of existence. When light meets matter, it doesn't always just bounce, glow, or heat. Sometimes it transforms. A single photon can rearrange the very architecture of a molecule, twisting bonds, flipping shapes, or even stitching new structures together. This is the quiet world of photochemistry, where light is not simply an observer but a sculptor, reshaping molecules with exquisite precision. When a molecule absorbs a photon, an electron is lifted to a higher energy state. For a fleeting moment, the entire balance of forces within the molecule changes. Bonds that were stable become strained, and atoms that once stayed in place begin to shift. The molecule now sits on a different potential energy surface, an excited state, and its landscape of stability has been redrawn. Paths that were impossible in the dark suddenly open up, leading to new products and new behaviours. These transformations often happen through regions called conical intersections, where two energy surfaces, the ground state and the excited state, come so close that the molecule can move from one to the other almost effortlessly. You might imagine them as tiny quantum doorways connecting one energetic landscape to another. At these intersections, the molecule can lose its excitation energy in an instant, releasing it as light or heat, or using it to trigger a chemical reaction. One of the simplest and most famous examples is isomerization, when a molecule changes its shape in response to light. The retinol molecule in your eyes, for instance, switches from a bent form to a straight one when struck by a photon. That tiny twist sets off a cascade of biological signals that eventually become vision. It's astonishing to think that your entire ability to see, from sunlight to colour to motion, begins with a single molecular flip, powered by a photon and guided through a conical intersection. Photochemistry also drives some of the grandest transformations on Earth. Photosynthesis, the process by which plants and algae turn light into chemical energy, begins when pigments such as chlorophyll absorb photons and transfer the energy through a series of reactions. The electrons, once excited, hop between molecules like well-choreographed dancers, storing sunlight's power in stable chemical bonds. That energy later becomes the oxygen we breathe and the food we eat. Every green leaf is a molecular solar panel, operating at near-perfect efficiency through photochemical mastery. Not all photochemical reactions are so benevolent. Ultraviolet light, for instance, can break chemical bonds directly, splitting molecules apart in a process known as photodissociation. It's why sunlight can fade fabrics, degrade plastics, and damage DNA. The same energy that sustains life can also quietly unravel it, depending on how it interacts with the molecular structure. In this sense, light is both artist and critic, creating and erasing with equal ease. Understanding these transformations requires a sense of timing almost beyond comprehension. The crucial motions, bond stretches, rotations, energy transfers, happen in femtoseconds, millionths of a billionth of a second. To study them, scientists use ultra-fast lasers, capable of producing pulses shorter than the vibration period of a single bond. These lasers act like strobe lights for molecules, freezing motion and revealing each stage of the reaction in slow motion. By sending a sequence of pulses and measuring the resulting spectra, researchers can watch a molecule absorb energy, twist, rearrange, and relax, all before it has time to blink, if molecules could blink at all. These pump probe experiments have turned chemistry into cinema at the quantum scale, where frames are femtoseconds long and motion unfolds faster than intuition can follow. The dream, however, goes beyond observation. Scientists are learning not just to watch reactions, but to control them, to use light as a conductor's baton in a molecular orchestra. By shaping the timing, intensity, and wavelength of laser pulses, they can nudge molecules towards specific outcomes, breaking one bond while leaving another intact, steering electrons down one path instead of another, even directing the flow of energy through a complex system. This control relies on a delicate principle called quantum coherence. When a molecule absorbs light, its electrons don't simply jump from one state to another. They enter a superposition, existing in several possible configurations at once. For a brief moment, these possibilities interfere with each other, like overlapping waves of probability. The challenge is that this coherence doesn't last long. Random vibrations and environmental noise quickly destroy it, a process called decoherence. Still, during its fleeting existence, often lasting only tens to hundreds of femtoseconds, coherence allows scientists to guide a molecule's evolution like an artist brushing light across a canvas. By designing laser pulses that match the molecule's natural vibrations, they can reinforce certain quantum pathways and suppress others. It's chemistry conducted with precision timing, a kind of music where the instruments are atoms and the notes are photons. Selective bond breaking is one of the most tantalizing applications. Imagine being able to shine a light on a complex molecule and have only one specific bond snap, leaving the rest untouched. Traditional heat-driven chemistry can't do that. It's like trying to melt a single letter off a wax seal using a bonfire. But with quantum control, the energy can be delivered exactly where it's needed, in just the right rhythm and phase to trigger a precise transformation. In practice, this field is still young. Coherence times are short, environmental interference is relentless, and the mathematics of control can be dizzyingly complex. But progress is steady. Already scientists have demonstrated control over simple reactions, guiding isomerizations and dissociations with carefully shaped laser pulses. In materials science and biology, researchers are beginning to explore how such control could one day lead to more efficient solar cells, advanced molecular machines, or even photodynamic therapies that target disease cells with surgical precision. It's a reminder that light is not merely an external force but an active participant in the molecular world. Every photon carries the potential to do work, to shift electrons, to alter geometry, and with modern tools we're learning to speak its language, to compose with it rather than simply observe. Even so, nature still outperforms us. Plants, bacteria, and even some animals have evolved to manipulate light with a grace that our lasers can only imitate. They funnel photons through pigment arrays, transfer energy without waste, and perform photochemistry with nearly perfect efficiency. In every green leaf, light has been conducting this molecular orchestra for billions of years. We're only now beginning to understand its score. The interplay between light and matter is one of the most profound relationships in science. It's the story of energy being passed hand to hand, of photons guiding electrons across quantum landscapes. Whether in the precision of laboratory lasers or the quiet rhythm of photosynthesis, the principle is the same. Light sets the tempo, and matter follows. So the next time sunlight filters through a leaf or glints off a surface, imagine the choreography unfolding within. Electrons moving in perfect synchrony, molecules reshaping mid-flight, and quantum rules composing the melody of transformation. Light doesn't simply illuminate the world, it directs it, and in its silent rhythm, chemistry finds its most elegant conductor. In the solid world, chemistry takes on a new kind of order. Instead of molecules drifting freely through space, atoms stand shoulder to shoulder, locked in vast repeating patterns. Their orbitals overlap, intertwine, and merge into collective systems that stretch across entire crystals. Here, individual molecules fade into the background, and new quantum behaviors emerge. Behaviors that give rise to metals, semiconductors, insulators, and almost every technology that shapes modern life. You could say that in the solid state, chemistry becomes architecture. At the atomic scale, each atom in a solid brings along its own set of orbitals, s, p, d, and sometimes f. When millions or billions of these orbitals overlap, the discrete energy levels of individual atoms blur together into continuous regions called bands. These bands define how electrons can move through the material. The lower region, where electrons fill up stable states, is called the valence band. The upper region, where electrons can move freely and conduct electricity, is the conduction band. The space between them, the forbidden zone where no electron states exist, is the band gap. The size of this band gap determines the material's personality. In metals, the valence and conduction bands overlap, leaving no forbidden zone at all. Electrons can drift easily under even a tiny electric field, which is why metals conduct so well. In insulators, the band gap is wide, too wide for electrons to jump across under normal conditions. Glass, diamond and pure silicon dioxide are examples. Their electrons are tightly bound, unwilling to roam. And then there are semiconductors, those fascinating materials that sit delicately between the two extremes. Their band gaps are narrow enough that electrons can be promoted from the valence band to the conduction band by modest amounts of energy, sometimes from heat, sometimes from light. This balance makes semiconductors both controllable and versatile, and it's why they lie at the heart of modern electronics. Pure silicon, for example, is a semiconductor with a modest band gap. At room temperature, only a few electrons have enough energy to cross from the valence band to the conduction band, creating tiny pockets of positive charge called holes where they came from. But we can change its behavior dramatically through a clever trick called doping. Doping means introducing small amounts of impurity atoms into the crystal lattice, not to ruin the structure but to fine-tune it. Add a touch of phosphorus, which has one more valence electron than silicon, and you create an N-type semiconductor rich in extra electrons. Add boron, which has one fewer, and you get a P-type semiconductor filled with positive holes. Where the two types meet, a fascinating boundary forms, a region where electrons and holes mingle, creating an internal electric field. This is the basis of the p-n junction, the beating heart of diodes, transistors, and nearly every chip inside your phone or computer. When light strikes a p-n junction, it can excite electrons across the band gap, generating a flow of charge. This is the principle behind solar panels. When electricity passes through it instead, electrons fall across the junction and release light, the working idea behind LEDs. Whether turning light into current or current into light, the same quantum dance of electrons plays both tunes. The subtle control offered by semiconductors has allowed humanity to build machines that think, calculate, and communicate. Every transistor on a microchip is in essence a gate for electrons, a switch that opens and closes depending on the voltage applied. Modern chips contain billions of these quantum gates etched into layers of silicon, copper, and insulating oxides, each only a few atoms thick. The flow of electrons through their band structures is what gives rise to all digital logic, from streaming videos to spacecraft navigation. Beyond semiconductors, the surfaces of solids tell another story, one of chemistry happening not inside but on materials. The outermost atomic layers of a solid are uniquely active. Their atoms, missing neighbours on one side, hold unsatisfied bonds and unbalanced charges. These exposed sites act as magnets for molecules, attracting them, binding them, and sometimes transforming them entirely. This is the realm of surface chemistry. The reason why finely powdered catalysts can accelerate reactions thousands of times faster than smooth blocks of the same material. In heterogeneous catalysis, the surface provides a stage where reactants meet, rearrange, and depart as products. Metals like platinum, palladium, and nickel are favourites because their surfaces can temporarily bond with molecules, stretch their bonds, and make them easier to break or remake. This process powers everything from the catalytic converters that clean car exhaust to the industrial synthesis of fuels and fertilizers. Even materials that seem inert are quietly interacting with their surroundings. The rusting of iron, the tarnishing of silver, the self-cleaning surfaces of modern coatings all depend on the microscopic chemistry of surfaces. The interface between a solid and its environment is never still. It's a living frontier where atoms trade electrons, energy, and structure. The same frontier drives technologies like batteries and fuel cells. In a lithium-ion battery, for instance, the charge you use to power your devices flows because lithium ions slip in and out of the atomic layers of solid materials. Each movement is a tiny act of surface chemistry: insertion, migration, release, repeated billions of times without you noticing. The efficiency, lifetime and safety of every battery depend on the smoothness and stability of these solid-liquid interfaces. Quantum effects also govern how materials absorb and emit light. The color of a semiconductor, for instance, is tied to the size of its band gap. A smaller gap yields redder light, a larger one bluer. By adjusting composition and structure, scientists can tailor materials to absorb or emit specific wavelengths. That's how LEDs of every color are engineered, from the soft glow of a night lamp to the bright white beams of a flashlight. Even the blue LED, invented in the 1990s, was a triumph of quantum materials science, a breakthrough that enabled modern screens, efficient lighting, and a Nobel Prize. Nanomaterials push these ideas even further. When particles shrink to the scale of a few nanometers, the boundaries between chemistry and physics blur. Quantum confinement, the restriction of electron motion within tiny spaces, alters the material's electronic structure. Gold, for example, appears yellow in bulk but turns red or purple at the nanoscale. Quantum dots used in high-end displays emit vivid, tunable colors based entirely on their size. Shrink the particle, widen the band gap, enlarge it, shift the emission toward red. It's chemistry painted with quantum precision. In the quiet stability of a solid, all the restless laws of quantum mechanics are still at play. Orbitals overlapping, electrons delocalizing, energy levels merging into bands. From those invisible interactions emerge the tangible world of wires, circuits, screens, and solar cells. It's humbling to think that every building, every device, every glint of metal or pane of glass is a symphony of electrons arranged in collective harmony. The strength of steel, the transparency of glass, the conductivity of copper, all flow from the same fundamental principles: how orbitals overlap, how bands form, and how electrons respond. So perhaps the solid state is not so solid after all. Beneath its apparent stillness, it's a realm of flowing electrons and dynamic surfaces, of interactions too small to see, but powerful enough to shape entire civilizations. The next time you touch a phone screen, switch on a light, or simply feel the weight of a metal object in your hand, remember, you're holding the quiet architecture of quantum chemistry, built atom by atom into something strong enough to shape the modern world. At first glance, biology seems far too large, warm, and noisy for quantum mechanics to matter. The delicate quantum effects that shape atoms and molecules are usually washed out by the jostling of thermal energy. Yet, if you look closely enough, the whisper of the quantum world still echoes in living things. It hums quietly inside enzymes, ripples through photosynthetic complexes, and perhaps even helps some animals find their way across the globe. It's not magic, it's meticulous biochemistry at its most refined. One of the most subtle quantum players in biology is the hydrogen bond. These bonds are weaker than covalent ones, but stronger than simple attractions, and they hold the double helix of DNA together, guide protein folding, and shape the water that fills every cell. At their core, hydrogen bonds depend on a delicate balance of charge and distance. The hydrogen atom involved, really just a proton with an attached electron, can shift between partners, sharing its presence in a kind of molecular tug-of-war. In many cases, that tug-of-war can turn into something even more remarkable: proton tunneling. In quantum mechanics, particles are never entirely confined. There's always a small chance they'll appear on the other side of an energy barrier without climbing over it. For protons, which are light and mobile, this means they can occasionally tunnel from one atom to another in an enzyme's active site. It's as if the proton slips through a wall that classical chemistry says should be impenetrable. This tunneling can make reactions faster, smoother, and more precise. Enzymes, those extraordinary biological catalysts that make life possible, often rely on networks of hydrogen bonds that guide protons with uncanny accuracy. In some cases, the measured reaction rates are too high to be explained by thermal motion alone, hinting that quantum tunneling is quietly lending a helping hand. The evidence for this comes partly from what's known as the isotope effect. Replace a hydrogen atom with its heavier cousin, deuterium, which has an extra neutron, and the reaction often slows down dramatically. The heavier isotope vibrates more sluggishly, making tunneling less likely. This difference provides one of the strongest fingerprints of quantum behavior in biology. It's not a miracle of physics, it's a precise dance of probability, happening billions of times a second inside every living cell. Quantum mechanics may even help explain how some of life's most complex processes achieve their astonishing efficiency. Consider photosynthesis, the process that powers nearly every ecosystem on Earth. When a photon of light hits a leaf, it excites an electron within the pigment molecule chlorophyll. That energy then travels through a network of proteins toward a reaction center, where it's stored in chemical form. For decades, scientists assumed this energy transfer was purely random, like a marble bouncing from one molecule to another. But experiments using ultra-fast lasers have revealed hints of something deeper. At temperatures even above freezing, some photosynthetic complexes appear to maintain quantum coherence, a state where the energy moves as a wave, exploring multiple paths simultaneously and interfering with itself to find the most efficient route. It's as if the excitation doesn't choose a single path, but samples them all at once, taking the fastest option before decoherence sets in. Now, this doesn't mean that plants are quantum computers in disguise. The coherence times measured are fleeting, often less than a trillionth of a second, and may arise from complex vibrational couplings rather than pure quantum effects. Still, the idea that nature exploits wave-like behavior to optimize energy flow is both elegant and deeply plausible. Evolution has had billions of years to refine molecular machinery. It's no surprise if it occasionally stumbled upon quantum tricks that even physicists admire. Another fascinating, though more controversial topic lies in the navigation of migratory birds. Many species seem able to sense Earth's magnetic field with uncanny accuracy, even on overcast days when visual cues vanish. One leading hypothesis suggests that this magnetic compass might arise from quantum spin effects inside special, light-sensitive proteins called cryptochromes. According to this model, when a photon strikes the cryptochrome molecule in a bird's retina, it creates a pair of electrons whose spins are quantum mechanically linked, a state known as a radical pair. The orientation of Earth's magnetic field subtly alters how these spins evolve and recombine, changing the chemical output of the reaction. If true, the bird's brain might interpret these molecular differences as directional information. It's a beautiful idea, that a robin's sense of north could depend on quantum spin dynamics unfolding inside its eyes. But scientists tread carefully here. While there's experimental support for the radical pair mechanism, the details remain uncertain, and alternative explanations may yet emerge. Quantum biology, for all its intrigue, still walks a narrow line between evidence and speculation. What's most inspiring, though, is not the potential for magic, but the reminder that life, in all its complexity, still obeys the same physical laws as everything else. Quantum effects don't break biology's rules, they refine them. They allow enzymes to be faster, photosynthesis to be more efficient, and perhaps some creatures to orient themselves using forces invisible to us. The skepticism around these ideas is healthy and necessary. Science thrives on cautious curiosity, on finding that balance between wonder and restraint. Some claims in the past have leapt too quickly from quantum strangeness to mystical interpretation. But the genuine quantum effects in biology are more subtle and far more interesting. Not dramatic violations of physics, but quiet collaborations with it. Take tunneling once more. It doesn't defy chemistry, it complements it. It's the same process that helps the sun fuse hydrogen into helium, the same principle behind nuclear decay and semiconductor design. Life, it seems, found a way to put that same phenomenon to work under much gentler conditions: room temperature, water-filled environments, and carbon-based molecules. That's not mysticism, that's mastery. The same goes for coherence and photosynthesis. The fragile, fleeting nature of these quantum states makes their persistence all the more remarkable. It's as though evolution learned to whisper to quantum systems without shouting loud enough to disturb them. The fact that it can even happen for a trillionth of a second inside a warm, noisy cell is extraordinary. These glimpses of quantum behavior in biology hint at something profound. Not that life is separate from physics, but that it is deeply embedded in it. Every breath, every heartbeat, every spark of metabolism depends on quantum laws playing out quietly beneath the surface. The molecules of life are quantum instruments, tuned by evolution to perform reliably, even amid the chaos of the living world. So, when scientists talk about quantum biology, it's not about mystery or magic. It's about humility. The realization that even the most familiar aspects of life still trace their origins to the strange, probabilistic rules of the subatomic realm. It's a reminder that the same principles governing electrons in a silicon chip or photons in a laser are also at work inside your cells, guiding the chemistry of existence itself. In the end, the frontier between biology and quantum mechanics isn't a sharp line at all. It's a soft edge, a region of overlap where life borrows just enough of the quantum world to make miracles look ordinary. Hydrogen bonds, tunneling protons, migrating birds, and glowing leaves all belong to the same grand tapestry, and perhaps that's the most beautiful thing about it, that life doesn't escape the quantum rules. It thrives because of them. Temperature may seem like one of the simplest concepts in science, a single number that tells us how hot or cold something is, but beneath that comforting simplicity lies a quiet quantum democracy. Every atom, every molecule, every vibration contributes to temperature, not as a uniform hum, but as a vast statistical chorus of motion and energy. Thermodynamics in this sense isn't about chaos defeating order. It's about how the tiniest quantum states find balance together. In the 19th century, the physicist Ludwig Boltzmann gave that balance a mathematical face. He realized that in any collection of particles, from a gas in a balloon to molecules in your coffee, energy doesn't sit evenly distributed. Instead, it's shared according to probability. Most particles occupy low energy states. A smaller number sit in higher ones, and the exact ratio between them is governed by what we now call the Boltzmann distribution. You can imagine it as a landscape of energy levels, valleys of low energy, hills of higher energy. At low temperatures, particles gather in the valleys, calm and still. As the temperature rises, more and more of them climb the hills, exploring new states. The hotter the system, the more adventurous the particles become. The beauty of the Boltzmann distribution is that it connects temperature, probability, and energy in a single graceful equation, one that describes everything from how molecules rotate and vibrate to how stars radiate light. This distribution is what makes chemistry predictable. It tells us which molecules in a reaction mixture have enough energy to climb the activation barrier and react. Even at room temperature, only a small fraction of molecules have the necessary push. But in a world with trillions upon trillions of collisions, that small fraction is enough. Heat doesn't make every molecule react. It simply gives more of them the chance. Boltzmann also gave us a way to understand one of science's most misunderstood concepts: entropy. In everyday language, entropy is often equated with disorder, but in physics, it's something subtler, a measure of how many ways the components of a system can arrange themselves while still appearing the same on the outside. A perfectly ordered crystal at absolute zero has only one possible arrangement, and thus minimal entropy. A gas, by contrast, can be organized in an almost infinite number of ways. Entropy is not the enemy of order, it's the quiet accounting of possibility. Boltzmann captured this idea in a deceptively simple equation. Entropy equals Boltzmann's constant times the logarithm of the number of microstates. Each microstate is a different microscopic arrangement, the positions and energies of every particle, that correspond to the same overall appearance. The more microstates available, the greater the entropy. It's a beautifully democratic principle. Nature doesn't prefer order or disorder, it prefers freedom. The freedom for systems to explore as many configurations as they can. And yet, entropy isn't just about spreading out energy, it's also the engine of spontaneity. When chemists talk about whether a reaction will happen on its own, they aren't just asking whether it releases energy, but whether the total entropy of the universe, system plus surroundings, increases. Sometimes a reaction can even absorb energy and still occur, as long as it creates enough new possibilities in the process. To capture this delicate balance between energy and entropy, we use a quantity called free energy, a measure that decides whether change is favourable under given conditions. Free energy is where spontaneity meets structure, where the push of energy and the pull of entropy negotiate their quiet treaty. It explains why ice melts at 0 degrees Celsius, why proteins fold spontaneously into precise shapes, and why some reactions wait patiently until the temperature or pressure changes just enough to tilt the balance. Temperature in this sense is a mediator, a translator between quantum behavior and macroscopic experience. At high temperatures, the differences between quantum energy levels blur, and classical physics takes over. But as temperature falls, the gaps between those levels become visible again. At extremely low temperatures, quantum effects reassert themselves with elegance and power. Consider helium, that gentle, colourless gas we use to fill balloons. Cool it to just above absolute zero, and it does something extraordinary. It becomes a superfluid. In this state, helium flows without friction, creeping up walls and escaping any container it can find. The atoms no longer act like individuals but merge into a single quantum wave function, moving as one coherent entity. You can spin a container of superfluid helium, stop the container, and the liquid will keep rotating inside. A quiet defiance of everyday intuition. It's as if the fluid forgets what resistance is. The same quantum strangeness appears in solids too. At low temperatures, the specific heat, the amount of energy needed to raise a material's temperature, behaves in ways that classical physics cannot explain. Instead of decreasing smoothly, it drops sharply, reflecting the discrete nature of vibrational energy levels. In a crystal, atoms vibrate in quantized patterns called phonons, waves of motion that carry heat and sound. As temperature falls, fewer phonon modes are excited, and the material grows eerily still. The familiar warmth of matter fades away, leaving behind the quiet hum of quantum motion that can never be fully silenced. Even entropy itself behaves differently in these extremes. Near absolute zero, most systems lose almost all their available microstates, approaching perfect order. Yet quantum uncertainty prevents them from ever becoming completely still. 0-point energy, the minimum possible energy dictated by the Heisenberg uncertainty principle, ensures that even at the coldest conceivable temperature, particles still quiver faintly, never quite at rest. Absolute zero is a destination that nature allows us to approach but never truly reach. It's humbling to realize that the great laws of thermodynamics, so broad, so macroscopic, are rooted in the quantum fabric of matter. Entropy arises not from chaos, but from the counting of quantum states. Temperature is not a mystical property, but an average of countless tiny motions. The direction of time itself, at least as we perceive it, may be tied to entropy's gentle insistence on exploring every available arrangement. And there's beauty in that partnership. Order and disorder are not enemies at war. They are partners in a cosmic dance. Order gives structure, disorder gives possibility. Without entropy, crystals would never melt, gases would never mix, and life would never evolve. Without structure, there would be no molecules to rearrange, no order to lose, no patterns to rediscover. You can see this balance in everyday life. Ice cubes melting into water represent not chaos, but change, molecules gaining freedom of motion. When steam condenses into droplets, entropy decreases locally, but only because energy and disorder are released elsewhere. Every process, from chemical reactions to cosmic evolution, plays out as an exchange between these two quiet principles. In a sense, thermodynamics is the story of how the universe learns to share. Heat flows from hot to cold until temperatures equalize. Entropy grows as possibilities multiply. Energy is conserved yet redistributed. At the smallest scale, quantum mechanics dictates the shape of each possibility. At the largest, thermodynamics counts them all and decides the outcome. The next time you feel warmth spreading through your hands, or watch frost vanish under the morning sun, you're witnessing that partnership in motion, countless quantum states reshuffling themselves toward balance. Order yielding to disorder, disorder giving rise to new forms of order. The two are not opposites. They are the yin and yang of existence, the gentle push and pull that keeps the universe alive and ever-changing. Quantum chemistry, for all its beauty, hides a mathematical monster beneath its elegance. The laws that govern electrons and nuclei are known. The Schrödinger equation tells us exactly how a molecule should behave. But solving that equation for anything larger than a hydrogen atom quickly becomes impossible. The culprit is the many-electron problem. Every electron in a molecule feels the pull of every nucleus and the push of every other electron all at once. The mathematics is perfectly clear, but the combinations of interactions explode exponentially. To compute them all exactly would take longer than the age of the universe, so chemists, ever resourceful, turn to approximations, clever shortcuts that preserve truth without drowning in detail. Over the 20th century, these methods transformed quantum chemistry from an impossible dream into a practical science. And with the rise of computers, the discipline entered its golden age, a realm where molecules could be designed, tested, and tweaked not in glassware, but in code. The first major step came with the Hartree-Fock method, developed in the 1920s and 30s. It was an elegant compromise. Instead of trying to calculate the tangled, simultaneous motion of all electrons, Hartree-Fock treated each one as if it moved independently in the averaged field of all the others. Each electron feels the collective presence of its companions, but not their moment-to-moment jitters. This simplifies the problem enormously, turning the impossible many-body equation into a manageable set of one-electron equations that are solved self-consistently. In this picture, every electron occupies a mathematical orbital, and the overall wave function of the system is built as a Slater determinant, a structured way to ensure that electrons obey the Pauli exclusion principle, never sharing identical states. The method is rigorous, systematic, and surprisingly accurate for many systems. It captures the structure and general energy of atoms and small molecules quite well. But Hartree-Fock has a blind spot. By treating electron interactions only in an averaged way, it misses the subtle correlations that arise from the dance of paired motions. When one electron moves, the others adjust in real time to stay out of its way. These correlations may seem minor, but they are essential for precision. Without them, predicted bond lengths can be off, reaction energies skewed, and molecular behavior misrepresented. To fix this, quantum chemists developed a family of more sophisticated methods collectively called post-Hartree-Fock techniques. These approaches reintroduce electron correlation in different ways, often at the cost of heavy computation. Configuration interaction, for instance, builds the total wave function as a combination of multiple electronic arrangements, not just one. Müller-Plesset perturbation theory, MP2, MP3 and beyond, adds corrections based on how the system would respond to small disturbances in its mean field environment. Couple cluster theory, one of the most accurate and respected methods, takes things further by including collective excitations of electrons in a way that approaches chemical perfection. Each of these methods scales steeply in computational cost, sometimes as the fourth, fifth, or even seventh power of the number of electrons. That's why even the fastest supercomputers occasionally need metaphorical coffee breaks when dealing with complex molecules. But when the calculations converge, the results can rival experimental accuracy, predicting reaction energies, bond angles, and spectral lines to astonishing precision. Still, the real revolution came when scientists decided to rethink the problem altogether. Instead of chasing the impossible many-electron wave function, what if we focused on something simpler, the electron density? After all, every measurable property of a system, from its energy to its shape, depends ultimately on how its electrons are distributed through space. In 1964, physicists Pierre Hohenberg and Walter Kohn proved a profound theorem. The ground state energy of any system is a unique functional of its electron density. This insight gave birth to density functional theory, or DFT. DFT flips the traditional approach on its head. Rather than solving directly for an unwieldy wave function that depends on 3 coordinates for each electron, DFT deals with a smooth electron density function, depending only on 3 coordinates total. This simplification turns a many-dimensional nightmare into a tractable problem, one that modern computers can handle even for large molecules and materials. At its core, DFT still needs approximations because the exact relationship between the electron density and the total energy, the so-called exchange correlation functional, remains unknown. But over decades, scientists have developed increasingly accurate functionals that balance simplicity and precision. Each one captures the subtle effects of electron repulsion, exchange symmetry, and correlation in slightly different ways. Some are local, focusing only on the density at each point. Others are global, incorporating gradients and kinetic effects. The alphabet soup of DFT, LDA, GGA, B3LYP, and countless others reflects decades of refinement and creativity. The success of DFT lies in its balance. It's accurate enough for most practical problems, yet efficient enough to handle systems with hundreds or even thousands of atoms. Chemists use it to predict molecular geometries, reaction mechanisms, infrared spectra, and electronic properties with remarkable reliability. When an experimentalist wonders how a molecule might behave before ever synthesizing it, DFT is often the first tool they reach for. Of course, DFT has its quirks. It sometimes struggles with weak van der Waals forces, fails to describe excited states accurately, and can be sensitive to the chosen functional. Yet its power and accessibility have made it a cornerstone of modern chemistry, materials science, and even biology. From designing new drugs to optimizing catalysts, DFT has become a universal language, one that bridges theory and experiment. Imagine trying to predict the geometry of a complex organic molecule. Hartree-Fock might give you a rough sketch. The bond lengths and angles will be close, but not perfect. Post-Hartree-Fock methods, if you can afford the computational time, will refine the picture with exquisite detail. DFT, on the other hand, will give you a very good estimate quickly, often within a few % of experimental values, and it can handle molecules large enough to matter in real-world chemistry. This interplay between accuracy and efficiency defines the entire field. For small molecules where precision matters, say, determining the heat of a combustion reaction to within a fraction of a kilocalorie, high-level correlated methods reign supreme. For larger systems such as proteins, nanomaterials, or solar cell components, DFT provides the necessary balance between feasibility and insight. Beyond DFT, the frontier continues to advance. New hybrid methods combine the strengths of wave function and density-based approaches. Quantum Monte Carlo simulations use random sampling to approximate electronic behavior with statistical rigor. Machine learning, the newest arrival, is beginning to predict potential energy surfaces and reaction pathways faster than ever imagined, training on vast databases of computed and experimental data. These developments have transformed how science is done. Entire molecules can be designed in silico before they're ever synthesized. Materials for batteries, catalysts, and solar cells can be tested virtually, saving years of experimental trial and error. Drug candidates can be screened for binding efficiency and toxicity long before the first vial is prepared. The laboratory of the future hums quietly in supercomputers, where electrons are modelled, bonds form and break in digital silence, and the chemistry of possibility unfolds one calculation at a time. It's easy to forget how recent this revolution is. When the first quantum chemistry calculations were attempted in the early 20th century, they were performed by hand, with slide rules and mechanical calculators. Today, the same computations run in seconds, embedded inside software packages accessible to anyone with a laptop. A discipline that once required patience bordering on sainthood now thrives on the pace of modern computing, so perhaps quantum chemistry deserves its own kind of humour. This is the only branch of science where even supercomputers need coffee. The equations are relentless, the electrons uncooperative, and the precision addictively demanding. Yet the rewards are enormous. Every time a molecule's behaviour is predicted correctly, every time a new material is designed from first principles, it's a quiet victory for human ingenuity, and for the partnership between mathematics, machines, and the quantum world itself. In the end, computational quantum chemistry isn't just about solving equations. It's about learning to listen to the whispers of electrons through silicon intermediaries. The tools may change, from Hartree-Fock to DFT to whatever comes next, but the goal remains timeless: to understand how matter builds itself, one calculation, one approximation, and one quiet insight at a time. For most of human history, the world beneath the visible was a mystery. We could infer the presence of atoms, calculate their properties, even describe their bonds with mathematics, but we could not see them. The atomic world was a place of imagination and equations, not of images. Then, in the late 20th century, something remarkable happened. Scientists learned how to see electrons, to touch individual atoms, and to map the invisible structures that form the foundation of matter itself. We began at last to explore the nanoscale world, not by looking with light, but by feeling and listening to the whispers between atoms. The first great leap came in 1981 with the invention of the scanning tunneling microscope, or STM. Unlike an optical microscope, which uses light waves far too large to resolve atoms, STM relies on one of quantum mechanics' most delicate effects, tunneling. When a sharp metallic tip is brought extremely close to a surface, within just a nanometer or two, electrons can tunnel across the tiny gap between them. This current depends exquisitely on distance. Move the tip closer by even the width of a single atom, and the tunneling current increases dramatically. By scanning this tip across a surface and measuring how the current changes, scientists can build up an image of the electron density, a map of where electrons are most likely to be found. The resulting images are astonishing. Rows of atoms lined up like beads, ripples of electronic waves around defects, even the subtle interference patterns formed by electrons scattering from impurities. For the first time, atoms were not theoretical constructs. They were landscapes we could explore. At first, STM images looked almost surreal. Hills and valleys rendered in shades of electric blue or golden amber. But those hills weren't atoms themselves. They represented regions of high electron probability. In a sense, STM doesn't show where the atoms are, but where their electrons prefer to linger. It's like photographing a crowd, not by where people stand, but by how often they pass a given spot. Still, the precision was breathtaking. Scientists could now see the structure of crystals one atom at a time and even rearrange them. In a famous demonstration, researchers used an STM tip to move 35 xenon atoms into position on a nickel surface, spelling out the letters IBM, each atom placed by hand, one gentle nudge at a time. Close on STM's heels came another breakthrough, atomic force microscopy, or AFM. While STM depends on electrons, AFM is more tactile. It feels the surface instead of scanning it electrically. A sharp tip, attached to a flexible cantilever, hovers just above a sample. As the tip moves across, atomic scale forces between the tip and the surface, attraction, repulsion, or van der Waals interactions, cause the cantilever to deflect. By measuring these deflections, scientists can reconstruct the topography of the surface with astonishing accuracy. AFM can image insulating materials that STM cannot, since it doesn't rely on electric current. It can also operate in air, liquids, and even inside biological systems. In recent years, AFM has reached the point where it can resolve individual chemical bonds. You can literally see the difference between single, double, and triple bonds, their lengths and orientations captured with nanoscopic precision. It's a kind of quantum braille, a way of reading the invisible by touch. Together, STM and AFM form the twin eyes of nanoscience. STM reveals where electrons roam, AFM reveals how atoms are arranged. Using them in tandem, researchers can not only image molecules but manipulate them, pushing or pulling single atoms to build new structures. This is the essence of nanotechnology, not merely observing the small but engineering it. Electron microscopy provides another complementary window into the nanoscale world. Instead of using photons, it uses electrons accelerated to high speeds. Because electrons have much shorter wavelengths than visible light, they can resolve details down to fractions of a nanometer, far beyond the limits of traditional optics. In a transmission electron microscope, or TEM, a beam of electrons passes through an ultra-thin sample, and the pattern of transmitted and scattered electrons is magnified into an image. In a scanning electron microscope, or SEM, electrons scan the surface, producing stunningly detailed pictures of textures and shapes. The images look almost sculptural, the ridges of pollen grains, the fine hairs of insects, the ordered lattices of crystals, all revealed in grayscale landscapes of startling clarity. Electron microscopy has given us our most detailed glimpses of everything from viruses and cell membranes to semiconductor interfaces and nanoparticles. It bridges the gap between biology and materials science, showing us that the same quantum world underlies both living and non-living matter. As we began to look more closely, new frontiers opened up, especially in the realm of quantum confinement. When materials are made so small that their dimensions approach the size of the electron's wavelength, their electronic properties change. Electrons can no longer move freely as in a bulk solid. They become trapped in tiny potential wells. These nanostructures, quantum dots, nanowires, and two-dimensional sheets, exhibit behaviours that are distinctly quantum in nature. A quantum dot, for example, is sometimes called an artificial atom. It's a tiny piece of semiconductor material, often just a few nanometers across, where electrons are confined in all three dimensions. This confinement quantizes their energy levels, making them behave like discrete atoms rather than continuous solids. The colour of light a quantum dot emits depends on its size. Smaller dots have larger energy gaps and glow blue, while larger dots emit red. This tunability has made quantum dots indispensable in modern display technology, solar cells, and even biological imaging. It's remarkable to think that what was once invisible to the human eye, electrons moving within solids, can now be not only seen but shaped. We can design materials whose colour, conductivity and reactivity emerge from quantum control rather than chemical composition alone. In many laboratories, scientists now use STM and AFM tips to manipulate quantum dots, build nanowires atom by atom, or probe the electrical properties of single molecules. Some even study how electrons flow through DNA strands or jump between metal contacts, using these microscopes as both instruments and tools for construction. At the frontier of this field, visualization has become more than seeing. It's understanding. By watching how electrons distribute across surfaces, researchers can test theories of bonding and reactivity in real time. The patterns that once lived only in quantum chemistry textbooks, orbitals, nodes, and standing waves, now appear as real images on a screen. The once invisible mathematics of quantum mechanics has taken on tangible form, yet there's something poetic about this progress. In learning to see electrons, we haven't conquered the quantum world, we've joined it. The pictures from STM and AFM are not snapshots in the ordinary sense. They're probability maps, records of likelihoods, delicate portraits of motion frozen by patience and precision. Every image is both true and abstract, a glimpse of something that exists everywhere and nowhere all at once. This ability to visualize the invisible has changed how we think about matter itself. At the nanoscale, surfaces become landscapes, and individual atoms become architecture. Materials are no longer passive objects, but intricate terrains of charge and vibration. The boundaries between physics, chemistry, and engineering blur completely. You could say that humanity has learned to see whispers, the faint signals that once lived only in theory, now rendered visible through the quiet touch of quantum instruments. Each atom on an STM screen, each ripple in an electron wave, is a reminder that the universe, even in its smallest forms, is both structured and alive with motion. So when we peer into these nanoscale worlds, we're not just observing matter, we're witnessing a dialogue between electrons and energy, between touch and theory, between imagination and reality. For the first time, the invisible has a face, and it is one of quiet beauty shimmering with the hum of the quantum world itself. Quantum chemistry began as a quest to understand the invisible, to describe in numbers and waves how atoms bind and molecules behave. Over the last century, it has evolved from chalkboard equations to supercomputer simulations. But now a new tool is emerging, one that doesn't just approximate quantum behavior, but embodies it. It's a computer built from the same rules that govern the atoms themselves, and it might just be the ultimate way to study chemistry: quantum computing. At its heart, a quantum computer works very differently from the machines we use today. Traditional computers process information using bits, zeros and ones, that exist in one state or the other. Every calculation, no matter how complex, ultimately boils down to long sequences of these binary decisions. A quantum computer, however, uses quantum bits, or qubits. And qubits have a remarkable property. They can exist in a superposition of 0 and 1 at the same time, If a classical bit is like a coin lying heads or tails on a table, a qubit is that same coin spinning in midair. Not one, not the other, but both until it's measured. Add another qubit and the possible states double. Add a few dozen, and the combinations exceed the number of atoms in the universe. It's this exponential growth that gives quantum computing its almost mythical potential. But the magic doesn't stop there. Qubits can also become entangled, a kind of quantum teamwork where the state of one qubit instantly influences another, no matter how far apart they are. This entanglement allows quantum computers to handle complex correlations in ways classical systems can only mimic with tremendous effort. And for chemistry, where the behavior of electrons is all about correlation, the way one particle's movement subtly affects another's, this is revolutionary. The dream is simple to describe but enormously challenging to achieve. Use a quantum computer to simulate molecules directly, solving their electronic structures without the approximations that even our best classical methods require. In theory, a modest number of qubits could represent the entire quantum state of a molecule, capturing every interaction, every energy level, every bond vibration, in perfect fidelity. In practice, we're still a long way from that goal. But the first steps have already begun. To simulate chemistry on a quantum computer, we start with a molecular Hamiltonian, a mathematical object that describes the total energy of a system in terms of its electrons and nuclei. This Hamiltonian must be mapped onto the quantum hardware, with each qubit representing parts of the system's wave function. The challenge is that real molecules contain many interacting electrons, each coupled to all the others. Encoding this tangled web of interactions into qubits without losing precision or overwhelming the hardware requires clever algorithms and approximations of their own. One of the most promising approaches is called the Variational Quantum Eigensolver, or VQE. The idea is both elegant and pragmatic. Instead of letting the quantum computer do everything, we divide the labour. The quantum part prepares and measures trial quantum states, while a classical computer, the kind sitting on your desk, uses those results to adjust parameters and minimise the energy. This iterative dance continues until the energy converges to the molecule's ground state, its lowest, most stable configuration. In essence, the quantum computer provides a new kind of calculator, one capable of sampling the complex quantum landscape that classical computers struggle to represent. The classical side, in turn, guides the search intelligently. It's a partnership, a hybrid workflow where each system plays to its strengths. Quantum computing supplies the creativity. Classical computing supplies the discipline. The first demonstrations of this approach have already been carried out. Simple molecules like hydrogen, lithium hydride, and beryllium hydride have been simulated on small quantum processors with results that match theoretical predictions. These are humble beginnings, the molecular equivalent of sketching with chalk before painting a mural, but they show that the concept works. Of course, today's quantum computers are still fragile. Qubits are sensitive to everything: temperature fluctuations, electromagnetic noise, stray vibrations, even cosmic rays. Most need to be kept near absolute zero to maintain coherence, and even then, they can only hold their quantum states for microseconds. Errors creep in constantly, requiring sophisticated correction methods that use many physical qubits to represent a single reliable logical qubit. This makes scaling difficult. To simulate a complex molecule accurately, we might need hundreds of logical qubits, which, with today's error correction overhead, could require millions of physical ones. We're not there yet. The field is in what scientists call the noisy intermediate scale quantum era, or NISQ for short. It's a landscape of imperfect devices, capable of small demonstrations but not yet of grand revolutions. Still, progress is steady. Each year brings more stable qubits, better algorithms, and clever error mitigation techniques. Researchers are finding ways to squeeze more accuracy from fewer resources, using hybrid quantum classical workflows that adapt dynamically to the limitations of current hardware. In many ways, it mirrors the early days of classical computing, the 1940s and 1950s, when rooms filled with vacuum tubes could barely manage what a pocket calculator does now. What mattered then, as now, was persistence, and even before full-scale quantum chemistry becomes feasible, these machines are teaching us something valuable: how to think differently. In traditional computation, we follow clear linear steps, one operation leading neatly to the next. Quantum algorithms, by contrast, embrace uncertainty. They explore many possibilities simultaneously, letting interference amplify the right answers and cancel the wrong ones. It's a form of computation that feels less like command and more like persuasion, coaxing the universe to reveal its own solutions. The potential applications stretch far beyond curiosity. Imagine being able to predict reaction mechanisms and molecular energies with exact accuracy, designing catalysts that waste no energy, drugs that bind perfectly to their targets, materials that conduct electricity with zero loss. Every industry touched by chemistry could be reshaped. Instead of synthesizing thousands of compounds in a laboratory and testing them one by one, scientists could simulate their properties directly, guided by quantum calculations that match reality molecule for molecule. There's a gentle irony here. Quantum chemistry began a century ago as an attempt to describe electrons using classical mathematics, a desperate effort to fit a quantum world into human equations. Now we've come full circle, building machines that think in the same probabilistic, wave-like language as the systems we study. In the future, chemists might not debug code so much as debug molecules, tuning their electronic configurations directly on quantum hardware until theory and experiment become indistinguishable. Even so, a healthy dose of realism is needed. Quantum computing is not a magic wand. It's a long-term endeavour that will take decades of development to reach its full potential. The road ahead is lined with noise, instability, and complexity. But every generation of scientists has faced its own impossible dream, and often, impossibility simply meant waiting long enough for the right tools to appear. For now, quantum computing remains both a promise and a puzzle, a glimpse of the next great horizon in the long story of chemistry. The fact that we can even manipulate individual qubits, entangle them, and use them to probe the same equations that describe molecules is extraordinary in itself. Each small success, each simulated hydrogen molecule, each corrected error, each fleeting moment of coherence brings us closer to turning possibility into practice. And perhaps it's fitting that the story ends here, with uncertainty and hope intertwined. Quantum chemistry began with questions no one could yet answer, about waves, probabilities, and invisible particles. Now it stands at the threshold of a new chapter, where the very uncertainty that once puzzled us becomes a tool for discovery. In the quiet hum of cryogenic chambers, amid the delicate dance of qubits flickering between 0 and 1, the future of chemistry is being written. It's not a future of certainties, but of possibilities, fitting, after all, for a science that has always found its beauty in the space between. Chemistry has always seemed on the surface like the study of the tangible, substances you can pour, weigh, heat, and mix. But beneath the clinking glassware and colourful reactions lies something far quieter and infinitely stranger. At its deepest level, chemistry is not about things, but about waves. It is about probabilities, patterns, and symphonies of motion that we can't see but can feel in the stability of every atom around us. The elements of the periodic table, the shapes of molecules, the colours of minerals, even the breath you just took. All of them are written in the same hidden grammar, the language of quantum mechanics. Electrons hum softly in their orbitals, bound not by solid lines or predictable tracks, but by clouds of possibility. Atoms breathe in silence, expanding and contracting through vibrations too small to sense. Molecules hold together through delicate compromises of attraction and repulsion, dances of charge and symmetry that play out countless times per second. From this invisible choreography, the solid, liquid, and living world arises. It is easy to forget that the stability of everything we touch depends on uncertainty. Every table, mountain, and molecule owes its existence to the fact that electrons cannot sit still, that they must occupy discrete energy levels, never collapsing into their nuclei. What feels fixed is actually the result of restless balance, a ceaseless quantum tremor holding the macroscopic world together. The ordinary is, in truth, extraordinary. Quantum chemistry is the quiet architect behind every chemical bond, every spectral color, every biological reaction. It doesn't shout or blaze, it whispers in equations and patterns of probability. Its beauty lies not in spectacle but in precision, the way it explains, without fanfare, how the tiniest interactions ripple outward to form oceans, clouds, and living cells. There's something deeply humbling about realizing that even the most familiar sensations, warmth, scent, color, are born from wave functions overlapping and exchanging energy. The redness of a sunset is an electron falling between quantized states. The softness of water, the bitterness of coffee, the sparkle of glass, all are consequences of the same quiet mathematics, the same disciplined chaos. And yet, despite its complexity, quantum chemistry has a kind of calm logic to it. It's not mystical or chaotic. It's structured, elegant, and consistent. It tells us that the world is both predictable and unknowable. Predictable in its patterns, unknowable in its details. You can never say exactly where an electron is, but you can always say how it will behave on average. That balance between certainty and uncertainty is what gives matter its reliability. It also gives science its humility. For all our equations, we're still guests in a universe that operates far beyond intuition. Every time a chemist models a reaction, a physicist measures a spectrum, or a biologist studies an enzyme, they're tracing the outlines of an unseen order, one that has been quietly at work since the first atoms cooled from the fires of the early cosmos. Quantum chemistry doesn't only describe the world, it connects it. The same principles that govern a hydrogen atom also shape the bonds in DNA, the structure of crystals, and the colours of nebulae. From the quantum foam at the foundation of space-time to the shimmering layers of a soap bubble, the same equations apply. It is unity disguised as diversity. And if all of this feels a little too serene to be practical, remember that the world we live in, everything from smartphones to solar cells, from medical imaging to molecular medicine, is powered by quantum chemistry in action. Transistors, LEDs, catalysts and batteries all work because electrons obey the same rules Schrödinger and Heisenberg once puzzled over. The universe may seem mysterious, but it's a very consistent mystery. There's a kind of gratitude that comes from seeing this, from realizing that every bit of matter, every flicker of light, behaves not randomly, but according to elegant probabilities that create order from uncertainty. The world doesn't need supervision or correction. It sustains itself beautifully through balance. The molecules in your body, the ones that let you breathe, think and rest, are already following that order perfectly. You never have to remind your cells to obey quantum mechanics. They've been doing it flawlessly for billions of years. Even when life feels messy, nature's underlying structure remains astonishingly precise. It's a comforting thought. that behind the noise and movement of daily life, there's an invisible calm. Chemistry is the art of that calm. Electrons finding balance, atoms forming bonds, energy flowing in and out of harmony. If you could listen closely enough, the world might sound like a great quiet orchestra, playing without pause, without conductor, yet never missing a note. Of course, not every quantum system behaves gracefully. Some electrons misbehave, some molecules refuse to react, and some calculations take supercomputers days to solve. But even those imperfections are part of the beauty, the proof that complexity emerges naturally from simple rules. The best operators, as the saying goes, leave no fingerprints. Your molecules just quietly get on with it. No drama, no noise, just endless, invisible precision. Quantum chemistry began with uncertainty and fittingly ends with possibility. It showed us that we don't need to know everything to understand something deeply, that the world can be both unknowable and meaningful at the same time, that even in its smallest parts reality is generous enough to be coherent. So as you lie in the dark, perhaps listening to the faint hum of the world outside, take a quiet breath and let it remind you of this, that even rest is beautifully controlled. Every inhale and exhale is a symphony of molecular interactions, oxygen binding, electron shifting, energy exchanging, all unfolding with perfect grace without your command. Electrons hum, atoms breathe, and the world in all its complexity holds its structure in silence. That silence is not emptiness, it's harmony, the quantum rhythm of existence, steady and unseen, sustaining everything. May your next breath remind you of that every still moment, every beat of your heart, every drift into sleep is part of the same quantum order, invisible, gentle, and utterly magnificent.